Imagine you are planning a road trip. You could drive your own car for total control, take a bus for a managed schedule, or hail a taxi for point-to-point service without driving yourself. In Azure, compute is exactly this choice, deciding how much infrastructure you manage versus how much the cloud handles for you. Getting this decision right determines your application's cost, performance, and scalability. If you misalign the model with your workload, you will either waste money on idle virtual machines or face throttling during sudden traffic spikes. Mastering this spectrum is essential for passing AZ-305 exam. We will explore the Azure compute spectrum, walk through practical code examples for functions and virtual machines, review best practices to avoid common pitfalls, and finish with specific exam tips for the AZ-305 certification. You will learn how to deploy a Python script using the as function app command and configure scale sets with real CPU thresholds like 70%. Understanding these configurations prevents unexpected billing spikes and ensures your architecture meets compliance standards before production deployment. Let's define a key term you will encounter constantly: the compute spectrum. This refers to the range of hosting models available in Azure, spanning from infrastructure as a service, where you manage the operating system, up to serverless, where you only focus on code execution. Understanding where a service sits on this spectrum is the foundation of all infrastructure design decisions. If you misplace a workload on the wrong tier, you will either handle unnecessary patching tasks or lose critical network configuration control. The exam heavily tests your ability to map requirements to the correct hosting model. To choose the right tool, we must compare the core options side by side. Virtual machines offer maximum control but require OS patching. App Service is a managed platform ideal for web apps and APIs. Containers like ICI and IKS package code with dependencies for portability. Finally, Azure Functions provide event-driven serverless execution where you pay only for usage. Misidentifying these boundaries leads to over-provisioned resources and inflated monthly bills. The certification exam requires you to match specific workload characteristics to the exact service tier that delivers optimal performance. Now let's look at how to select the right compute for your specific needs. We start by assessing whether you need deep OS control or just code execution. Next, we evaluate the workload type to see if it fits web, container, or event patterns. Finally, we plan the scaling strategy to ensure reliability and cost efficiency. Skipping this evaluation often results in single points of failure during peak traffic. The AZ-305 exam consistently tests your ability to architect resilient systems that automatically adapt to changing demand without manual intervention. This step involves matching your workload to the service. For event-driven logic, Azure functions are often the best fit. Here is a Python function that triggers on an HTTP request. It extracts a name parameter and returns a personalized response, demonstrating how simple code runs without managing any underlying servers. You can deploy this using the as functions app command with a consumption plan set to 1 worker. Failing to configure proper timeout limits will cause silent failures during high-volume batch processing and trigger costly retry loops. We continue by evaluating the workload type. If you are building microservices, containers offer portability across environments. For web applications, managed platforms reduce operational overhead. We look at whether the task is long-running or short-lived to pick between VMs and serverless options. Misjudging duration often leads to terminated sessions during complex database migrations. The certification exam expects you to recognize that long-running processes require dedicated virtual machines with scheduled maintenance windows, properly configured for high availability. This evaluation often leads to infrastructure as code for reproducibility. Here is a bicep snippet defining a Linux virtual machine. It specifies the resource location, VM size, and OS profile. Using ISC ensures that your compute resources are version-controlled and consistently deployed across environments. You will typically run bicep build to compile the template before deploying with as deployment group create. Skipping validation steps frequently causes orphaned resources that continue generating unexpected monthly charges and violate compliance audits. Finally, we plan the scaling strategy to ensure reliability. We configure auto-scale rules to add instances based on load rather than resizing single machines. This approach improves fault tolerance and optimizes costs by aligning capacity with actual demand. You should set minimum instance counts to 2 for production workloads running behind a standard load balancer. Neglecting this configuration creates a critical bottleneck that will immediately crash your application during sudden traffic surges and trigger expensive support tickets. Once you have selected your compute, best practices guide the implementation. Always start with PaaS or serverless options to reduce management overhead. Use auto-scale rules that favor scale-out over scale-up for better reliability. Right-size your resources by monitoring utilization and downsize underused VMs to save costs. Ignoring these guidelines frequently results in performance degradation during peak hours and violates strict security compliance requirements. The exam consistently rewards architects who prioritize managed services to minimize operational risk and accelerate deployment cycles. Remember this principle: more control equals more management responsibility. When you choose virtual machines, you gain flexibility but accept the burden of patching and maintenance. When you choose functions or app service, you trade some control for higher developer productivity and lower operational overhead. This trade-off directly impacts your monthly cloud spend and team velocity. Failing to document these architectural decisions will cause confusion during certification scenarios that test your ability to justify infrastructure choices under strict budget constraints. Let's check your understanding. Which Azure compute service is best suited for running event-driven background jobs where you want to pay only for execution time? Is it virtual machines, app service, or Azure functions? Think about the serverless model we discussed. The correct answer is Azure functions because it automatically handles infrastructure provisioning and billing per millisecond. Selecting a virtual machine here would waste resources and complicate your scaling architecture during peak processing windows and violate cost optimization principles. We have covered the Azure compute spectrum, from IaaS to serverless. You learned how to compare services like VMs, app service, and functions based on control and workload. We reviewed code examples for functions and bicep and discussed best practices like right-sizing and auto-scaling to optimize cost and performance. Mastering these concepts ensures you can confidently navigate complex certification scenarios involving hybrid cloud architectures. Properly matching services to requirements prevents costly rework and guarantees reliable application delivery. For the AZ-305 exam, focus on matching workloads to the correct compute service. You will face scenarios asking you to choose between VMs and app service based on requirements for OS access or management overhead. Pay attention to keywords like serverless, container orchestration, and event-driven to identify the intended solution quickly. Practicing with real CLI commands and reviewing official documentation will strengthen your decision-making speed. Missing these contextual clues often leads to selecting over-provisioned resources that fail compliance checks. Picture yourself packing for a move. You have boxes of different shapes that must fit into a moving truck. If they are too small, you break dishes. If they are too big, you waste space and pay more. You must map application requirements to specific Azure VM families like the DSV3 series. Get it wrong, and you either crash your workload or burn cache on idle vCPUs. Today, we will figure out how to size your infrastructure perfectly. Here is our plan for the next few minutes. We will start by looking at the 4 core resource pillars that define a VM. Then we will dive into workload-specific sizing strategies for web and database servers. Next, we will walk through an infrastructure as code example using Terraform or Azure CLI to automate your choices. Finally, we will cover best practices and common pitfalls like right-sizing thresholds to watch out for on the exam. This structure guarantees exam success and prevents expensive cloud waste. When you design a VM, you are evaluating 4 primary dimensions. First is compute, which measures processing power via virtual CPUs allocated through the Azure Compute API. Second is memory, the RAM that holds your active data and code for fast access. Third is storage, where we look at IOPS using managed disks like Premium LRS. Fourth is networking, which dictates bandwidth via standard NICs. A key stat to remember is that the operating system typically consumes 1.5 gigabytes of RAM, requiring immediate buffer allocation before sizing your application workload. Let's define a term you will see constantly on the exam: vCPU. A virtual CPU is not a physical core sitting inside the hardware box. Instead, it is a hyper-threaded slice of a physical core managed by the hypervisor. Most cloud providers use a subscription ratio, often around 4:1. This means 4 virtual CPUs share the same physical thread. Understanding this distinction is vital because you cannot equate vCPU count directly to raw performance without considering hardware generation. Misjudging this ratio will cause CPU credits to deplete rapidly in burstable B-series VMs during peak traffic. Cloud providers offer different instance families based on your workload type. General-purpose D-series instances balance compute and memory, making them great for web servers and light applications. Compute-optimized F-series instances give you a higher ratio of vCPUs to memory, which is ideal for batch processing and gaming. Memory-optimized E-series instances provide massive RAM relative to CPU, perfect for in-memory databases and caching. Selecting incorrectly forces immediate budget overruns and triggers unexpected billing alerts during peak business hours. Here is how the sizing decision flows in practice. You start by identifying the workload type, such as a web server or a database. From there, you select the appropriate instance family based on that classification. Once the family is chosen, you check the performance metrics against your baseline requirements using Azure Monitor. Finally, you validate the cost against your budget constraints before deploying. Skipping this validation often leads to over-provisioned environments that trigger unexpected billing alerts and waste organizational cloud spend. Let's walk through the process of provisioning a sized VM step by step. First, you assess the CPU needs based on the workload intensity. This sets the baseline for how many vCPUs you will request. You would typically run the Azure CLI command as VM create with the size parameter to specify your exact tier. Getting this calculation right prevents resource contention during load testing and ensures your deployment aligns with enterprise compliance standards before it ever hits production networks. This Terraform block shows how you define that sizing in code. We specify the instance type as T3 medium, which gives us 2 vCPUs and 2 gigabytes of memory. The root block device sets a 50 gigabyte volume with GP3 storage for balanced performance. Tags help us track this resource as a production web server. Using precise ISC definitions prevents configuration drift across environments and ensures your deployment pipeline consistently provisions the exact compute tier required to meet strict SLI targets without manual intervention. Next, we allocate memory. For databases, you prioritize RAM to keep indexes in memory and avoid swapping. For web servers, balanced memory is usually sufficient. You should configure the memory parameter explicitly when using Cloud Shell scripts to reserve dedicated resources for critical processes. Failing to allocate adequate memory will force the kernel to swap active pages to disk, causing severe latency spikes and potentially crashing your application during sudden traffic surges. When you are sizing memory, look at the application requirements plus the operating system overhead. If your database needs 4 GB of working data and the OS takes 2 GB, you should provision a 6 GB instance minimum. This prevents the performance cliff that happens when the system starts swapping to disk. You must always add a 20% buffer for background services like antivirus agents and monitoring daemons. Ignoring this buffer will cause out-of-memory exceptions and trigger automatic restart policies during peak business hours. Third, we configure storage IOPS and throughput. Databases require high IOPS for random reads and writes. Large file processing benefits more from high throughput in megabytes per second. You should explicitly set the SKU Premium LRS parameter to guarantee consistent latency under heavy load. Misconfiguring this setting will cause random read delays that cascade into application timeouts and break transactional integrity across your distributed systems. For storage, choose the volume type based on the workload. Use provisioned IOPS SSDs for critical databases where latency matters most. Use standard SSD or GP3 volumes for general workloads to keep costs down. Always separate your OS drives from your data drives to make backups easier and prevent a full data drive from crashing the operating system. This separation ensures that disk space exhaustion on your logs never compromises core application availability or corrupts critical boot files during routine maintenance windows. Finally, we set the network bandwidth. High-traffic applications may require enhanced networking or larger NICs to handle the load without dropping packets. You should enable accelerated networking through the Azure portal to bypass the hypervisor and reduce CPU overhead. Neglecting this configuration will cause packet loss during high concurrency, IPI calls, and degrade user experience across your global endpoints significantly. Remember this principle: scale out, not up. Adding more instances to handle load provides better fault tolerance than making a single instance larger. If one node fails, your system stays alive. This approach is much easier to justify and manage in the long run. Implementing an Azure load balancer or application gateway distributes traffic evenly across multiple VMs. Relying solely on vertical scaling creates a single point of failure that will cause complete service outages during hardware maintenance or unexpected crash events. Let's check your understanding. You are deploying a database server that requires 4 GB of working memory. The operating system typically uses 2 GB. What is the minimum RAM you should provision to avoid performance issues? The correct answer is 6 GB plus a 20% buffer for background processes. This calculation ensures you stay below the critical memory threshold during peak query loads. Failing to account for this overhead will trigger automatic restarts and corrupt your transaction logs during high-demand business hours. We covered a lot of ground today. You learned the 4 core pillars of VM design: compute, memory, storage, and networking. We looked at workload-specific sizing for web and database servers. We walked through an infrastructure as code example to automate your choices. And we reviewed best practices like right-sizing iteratively and separating concerns. Mastering these concepts ensures you can confidently architect scalable solutions that pass certification exams and meet strict enterprise performance benchmarks without overspending on unused cloud resources. For the exam, focus on these tips. Always read the workload type carefully before choosing an instance family. Watch out for licensing costs tied to vCPU counts, as this can impact your total cost of ownership. Remember that right sizing is iterative. You should monitor metrics for 30 days and adjust resources accordingly. Finally, distinguish between vertical scaling and horizontal scaling when fault tolerance is mentioned. These distinctions directly map to scenario-based questions, where selecting the wrong answer will immediately eliminate your certification path. Imagine a highway toll booth during rush hour. You open extra lanes to keep traffic moving, then close them at night to save on staff costs. Running production infrastructure without auto-scaling is like trying to manage that traffic with a fixed number of lanes. Either you waste resources sitting idle, or your users get stuck in a jam when demand spikes. In this lesson, we will explore how Azure Virtual Machine Scale sets solve this problem by automatically adjusting capacity to match real-world load. We will cover the core architecture and orchestration modes of scale sets first. Next, we dive into implementing auto-scaling rules using the Azure CLI and JSON configurations. Then, we look at advanced strategies like predictive scaling and custom metrics from application insights. Finally, we review best practices to ensure your solution is robust for the AZ-305 exam, preventing costly overprovisioning during unexpected traffic surges. A virtual machine scale set acts as a template for your infrastructure. You define the OS image, VM size, and networking once, and the scale set orchestrates the lifecycle of every instance within it. This allows you to deploy hundreds of identical, load-balanced VMs in seconds. The real power comes from elasticity. You can scale out during peak hours and scale in during lulls to optimize costs. Azure supports up to 1,000 instances per set, making it ideal for large-scale cloud-native applications where manual management would fail. Let's define the key term you will see on the exam. A virtual machine scale set is a compute resource that lets you deploy and manage a group of identical, load-balanced VMs in seconds. It provides the ability to automatically scale based on demand or a defined schedule. Unlike a single VM, this resource abstracts the underlying instances, allowing you to focus on the application logic rather than individual server maintenance, which prevents configuration drift across your environment. Now let's look at how to implement auto-scaling rules. We will walk through this procedure step by step. First, you must define the metric trigger that tells Azure when to react. This involves selecting a specific metric like percentage CPU and setting a threshold condition. You will typically set a warning threshold at 60% and an action threshold at 75% to prevent premature scaling events that waste compute credits. Here is the Azure CLI command to add a scale-out rule. We use as monitor autoscale rule, create targeting our resource group, and autoscale name. The condition specifies that when the percentage CPU exceeds 70% on average over 5 minutes, we should scale out by one instance. This directly implements the metric trigger we discussed, ensuring your web tier handles sudden IPI spikes without dropping requests. Next, we set the scale action and configure the cooldown. The action defines whether we scale out or scale in and by how many instances. Crucially, we must add a cooldown period to prevent flapping. Without a cooldown, rapid threshold crossings can cause the system to constantly add and remove VMs, wasting resources and risking instability. A standard 300-second cooldown gives each new instance time to warm up properly. This JSON snippet shows the structure of an auto-scale profile in a deployment template. Notice the profiles array containing rules. Each rule has a metric trigger with the dimension and threshold, and a scale action that specifies the type and cooldown duration. The cooldown ensures the system waits before evaluating the next change, stabilizing the infrastructure, and preventing cascading failures during network blips or brief processing delays. When creating a scale set, you must choose an orchestration mode. Uniform mode is optimized for large-scale workloads where all VMs are identical. Flexible mode allows you to mix different VM sizes or use spot VMs for cost savings. Choose flexible if you need granular control over individual instances or want to run mixed workloads within the same set, which prevents vendor lock-in and simplifies complex dependency management. Beyond simple CPU metrics, modern architectures use advanced strategies for better performance. Schedule-based scaling pre-provisions instances before known traffic spikes, like Monday mornings. Predictive autoscaling uses machine learning to analyze historical patterns and scale proactively before demand hits. Custom metrics let you scale based on application-specific signals, such as service bus queue depth, ensuring your backend never bottlenecks during critical batch processing windows. Let's check your understanding. What happens if you set scale-in and scale-out thresholds too close together? Think about the behavior of the system when the metric hovers right at the boundary. If the gap is smaller than 10%, you will trigger constant scaling events that drain your budget and cause application restarts, ultimately degrading user experience during peak hours. Visualize the data flow of an autoscaling event. First, Azure Monitor collects metrics from your VMs. Next, the Autoscale service evaluates these metrics against your defined rules. If a threshold is crossed, it triggers a scale action to add or remove instances. Finally, the load balancer updates its backend pool to distribute traffic to the new or remaining healthy VMs, ensuring zero downtime during capacity adjustments. To ensure your scale set is production-ready, follow these best practices. Always use stateless applications so data loss does not occur during scale-in events. Implement graceful shutdown to finish processing requests before termination. Use custom images from tools like Packer to speed up provisioning, and always place your scale set behind a load balancer for even distribution, preventing single-node failures from taking down your entire service tier. Remember this principle as you design your solutions. Elasticity is key. Align infrastructure costs with actual user demand. Autoscaling should not just be a technical feature, but a strategic tool to optimize both performance and budget. By tying scaling rules to business KPIs, you guarantee that every compute dollar directly supports revenue-generating activities rather than sitting idle during quiet hours. Let's recap the key takeaways. VM scale sets provide high availability and elasticity by managing groups of identical VMs. Implementing autoscaling requires defining metric triggers, setting scale actions, and configuring cooldowns to prevent flapping. Advanced strategies like predictive scaling and custom metrics offer deeper control. Finally, ensure your apps are stateless and use custom images for optimal performance, which directly impacts your certification exam score and real-world deployments. For the AZ-305 exam, focus on these critical points. Know the difference between uniform and flexible orchestration modes and when to use each. Understand the importance of cooldown periods to avoid flapping. Be prepared to identify state management pitfalls and recognize the need for external databases in scale-in scenarios. Finally, remember to check subscription quotas before scaling out, as hitting limits will immediately block your deployment pipeline. Imagine a massive distribution center handling thousands of packages every hour. You wouldn't ask one worker to sort them all alone. You'd need an automated system that assigns packages to multiple workers simultaneously and tracks every step. That is exactly what Azure Batch does for your compute workloads, managing the chaos so you can focus on the results. In this lesson, we will explore the core architecture of Azure Batch, walk through a practical implementation workflow using the Python SDK, and cover critical best practices for cost optimization and reliability. We will also highlight common pitfalls to avoid on the AZ-305 exam. Understanding these components prevents costly misconfigurations when you deploy large-scale workloads in production environments. Azure Batch is a managed platform service designed specifically for large-scale parallel and high-performance computing workloads. It automatically provisions virtual machines using commands like as-batch pool create, installs required applications, and schedules jobs across those nodes efficiently. This automation prevents manual configuration drift and ensures your compute resources scale predictably during peak processing windows without overwhelming your infrastructure budget. To design a solution effectively, you must master the 4 primary components of the batch architecture. The batch account serves as your top-level resource group container. The pool holds the actual compute nodes where processing occurs. A job groups related tasks logically, while a task represents the smallest executable unit on a node. Misunderstanding this hierarchy causes billing leaks when tasks run on unintended pools. When designing your pools, you have 2 distinct VM options that behave very differently. Standard VMs guarantee availability and are ideal for critical workloads that cannot be interrupted. Low-priority VMs function as spot instances, offering up to 90% cost savings, but can be reclaimed by Azure if capacity is needed elsewhere. Choosing incorrectly causes unexpected job failures during peak regional demand. The data flow in a typical batch solution follows a clear sequence. First, you upload application code and input data to Azure Blob Storage. Next, you create a pool of compute nodes using as-batch node add. Then, you submit a job containing multiple tasks. Azure Batch automatically pulls the data from storage, executes the tasks across distributed nodes, and stores output back into your account, preventing network bottlenecks if regions mismatch. Let's walk through the implementation steps for a batch workflow. First, we provision the pool to define our compute capacity and node configuration using as-batch pool create with parameters like VM size standard D2S v3 and target dedicated nodes set to 10. This initial step establishes your baseline scaling limits and directly impacts how quickly your workload begins processing incoming data requests. Here is how you initialize the batch client and define a pool in Python. You create a cloud pool object specifying the VM size and target node count, then add it to the service. Immediately after, you define a job that links to this specific pool ID, ensuring tasks know where to run. Failing to bind the job correctly causes execution errors and wasted compute credits. Next, we move to the job level. Once the pool is ready, you create a job to group your tasks and define common settings like environment variables for credential management. This ensures all tasks in the job share the same configuration context. Skipping this step forces developers to hardcode sensitive values directly into task scripts, creating severe security vulnerabilities during audits. Now we add the actual work. You create a task-add parameter that specifies the command line to execute on the node using as-batch task create. This command runs against the input data and produces output. In production, you would use task-add collection parameter to submit tasks in batches for better IPI performance. Ignoring batch submission throttles your queue and delays critical reporting deadlines. Finally, we handle the execution and monitoring. Azure Batch automatically schedules these tasks across the pool nodes based on availability using built-in schedulers. You monitor metrics like pending tasks to ensure your scaling policy aligns with the actual workload demand. Neglecting this oversight causes node starvation during peak loads or unnecessary spending when queues remain empty for extended periods. To optimize your solution, focus on cost and performance. Always use low-priority VMs for fault-tolerant workloads to save up to 90%. Enable auto-scaling formulas like target task, count equals 50 to grow the pool when the queue is long and shrink it when idle. Keep your storage account in the same region as your pool to minimize latency and egress costs during heavy data transfers. Remember this principle: design your tasks to be idempotent. In distributed computing, nodes will fail unexpectedly. If a task fails and is retried, it must produce the exact same result without corrupting data or duplicating records. This ensures reliability even when infrastructure is volatile, preventing cascading failures that would otherwise invalidate your entire processing pipeline during certification scenarios. Here is a JSON configuration snippet for a start task. This runs on every node before any user tasks execute using as-batch pool update. You can use it to install software dependencies like apt-get packages or pip libraries, ensuring every node is fully prepared before processing begins. Skipping this configuration causes runtime errors when scripts reference missing binaries or unconfigured environment paths. Avoid common pitfalls that plague batch solutions. Never hardcode paths. Use environment variables like AZ-batch task working dir to locate files dynamically across different node configurations. Ignore failure handling at your own risk, and always ensure tasks are idempotent. Finally, monitor pending tasks metrics to prevent overprovisioning nodes when the queue is empty, which directly wastes budget during low-traffic maintenance windows. Let's check your understanding with a practical scenario. You have a large-scale image processing workload that can tolerate interruptions. Which VM type should you choose to minimize costs, and how does batch handle node reclamation? Selecting low priority, VMs reduces expenses significantly, while batch gracefully terminates nodes by saving state before shutdown to prevent data loss during capacity reallocation. We have covered the essentials of Azure Batch. It remains the definitive service for high-throughput parallel processing across distributed environments. Decouple your compute from storage, structure workloads for independence, and control costs with auto-scaling and low-priority VMs. Always design for failure by implementing retries and idempotent tasks, which guarantees consistent exam performance and production reliability under heavy load conditions. For the AZ-305 exam, focus on the distinction between batch and other compute services. Know when to use batch for HPC versus Azure functions or VMSS based on workload duration and parallelism requirements. Understand the hierarchy of account, pool, job, and task thoroughly. Remember that low-priority VMs are reclaimable but cost-effective, and always secure secrets using managed identities rather than hard-coding them in scripts. Imagine you are renting office space for a growing startup. You need to decide how many desks to buy, where to place them, and whether different teams share the same floor or have their own suites. Azure App Service plans work exactly like that physical infrastructure. They define the compute resources, region, and scaling capabilities that power your applications. In this lesson, we will master the design of these plans to build resilient, cost-effective cloud architectures. Skipping proper sizing causes crashes during spikes and bleeds money from idle VMs. Here is our roadmap for mastering app service plans. We will start by defining what an IESP is and its core components. Then we will compare the available tiers to understand their features and costs. Next, we will walk through a design strategy for isolating workloads using a cumulative approach. After that, we will implement these designs using Azure CLI commands. Finally, we will cover monitoring, scaling rules, and exam tips to ensure you are ready for the AZ-305. Failing to map tier capabilities to workload requirements leads to overprovisioning costs or unexpected downtime. Let's define the key term. An app service plan is a set of virtual machine instances configured to run and scale Azure App Service apps. It determines the region where your app lives, the instance size which defines CPU and memory, and the scale count which specifies how many VMs run your code. Every web app you create must be assigned to an app service plan. Misconfiguring the SKU or scale limits directly impacts your application response times and monthly billing totals. Azure offers a tiered model to suit different needs. The free and shared tiers are for testing only, with no custom domains or SSL support. Basic tiers handle lower traffic without autoscaling. Standard is the entry point for production, supporting autoscaling and deployment slots. Premium tiers offer high-performance hardware and advanced networking. Isolated provides dedicated hardware for maximum security. Choosing a tier below Standard for live customer traffic will block essential features like slot swapping and cause severe performance bottlenecks during load spikes. Visualize how traffic flows through your app service plan. A user request hits the load balancer, which distributes it across available VM instances in the plan. Each instance runs your application code and communicates with backend services like databases. The plan manages the health of these instances and scales them out based on metrics you configure. Ignoring health check endpoints or misplacing the load balancer configuration will cause routing failures and leave orphaned requests waiting indefinitely for timeout errors. Now let's design isolated workloads using a step-by-step approach. First, you separate production from development by assigning each environment to its own app service plan. This prevents heavy load tests in QI from consuming resources needed by your live users. Combining environments into a single plan risks noisy neighbor scenarios where debugging sessions suddenly throttle critical customer transactions and trigger cascading timeouts. Here is how you implement separation in code. This bicep snippet creates two distinct app service plans. One is named Prod Plan with a standard SKU for your live application. The other is Dev Plan, also standard but reserved for testing. By defining them separately, you ensure that resource allocation for production is never compromised by development activity. Forgetting to assign the correct plan ID to each web app will cause deployment failures and force manual runtime patches across multiple subscriptions. Next, you right-size your plans based on metrics. You start with a modest tier and use monitoring data to guide scaling decisions. If CPU usage is consistently low, you can scale down to save costs. If memory hits high thresholds, you scale up or out to maintain performance. Skipping metric analysis before adjusting instance counts often leads to overprovisioned VMs that waste budget or underprovisioned cores that trigger application crashes during sudden traffic surges. This JSON snippet configures an auto-scale profile to automate right-sizing. The capacity section sets a minimum of 1 and a maximum of 5 instances. The rules trigger scaling actions based on CPU percentage. When CPU exceeds 70% for 5 minutes, the system adds an instance. When it drops below 30% for 10 minutes, it removes one. Misaligning cooldown periods with your application startup time will cause rapid scale oscillations that waste compute resources and degrade end-user experience. Let's implement these designs using Azure CLI. First, you create a resource group to contain your plan. Then you create the app service plan with a standard SKU and Linux runtime. Finally, you deploy a web app to that plan, specifying the runtime version. This script ensures your infrastructure is reproducible across environments. Omitting the SKU parameter or mismatching the runtime string will trigger command failures and force manual portal corrections during critical release windows. Monitoring and scaling rules are critical for maintaining performance. Use Azure Monitor to track CPU and memory usage. If average CPU stays below 20%, you are likely overprovisioned and paying for idle capacity. Conversely, if memory hits 80%, you need to scale up or out. Enable deployment slots for zero downtime swaps, allowing you to test staging versions before swapping them into production. Neglecting alert thresholds will cause delayed incident responses and allow minor latency spikes to escalate into full service outages. Let's check your understanding. Which app service plan tier is the minimum requirement to support deployment slots? Think about the features we discussed for each tier. Deployment slots are a key feature for zero downtime deployments, so they require a production-ready tier. Selecting a basic or shared tier will block slot creation entirely and force you to rebuild your entire CI pipeline from scratch to meet compliance standards. Here is a principle to remember. Isolation protects performance, while automation manages scale. By separating workloads and configuring autoscale rules, you build an architecture that is both resilient and cost-effective. Ignoring these foundational practices will cause resource contention across environments and trigger unpredictable billing spikes when uncontrolled scaling events consume your entire monthly compute allowance without proper alerting mechanisms in place. Let's recap the key takeaways. Always isolate production from development by using separate app service plans to prevent noisy neighbor issues. Right-size your plans based on metrics, starting modestly and scaling as needed. Choose tiers based on business requirements, using standard for most production apps. Finally, use infrastructure as code to ensure consistency across environments. Skipping these steps will result in fragmented configurations that fail automated compliance audits and increase operational overhead during incident response procedures. For the AZ-305 exam, focus on tier features and scaling limits. You should know which tiers support auto-scaling, deployment slots, and VNet integration. Understand cost optimization strategies, such as right-sizing and cleaning up unused plans. Pay attention to region selection, ensuring your app service plan is in the same region as your database to minimize latency. Misreading exam scenario constraints will lead you to select unsupported tier combinations and overlook critical cost governance requirements. Imagine you are driving a car on a busy public highway versus a dedicated private tunnel. On the highway, you share lanes with unpredictable traffic, but that private tunnel gives you total control over access and speed limits. In Azure App Service, standard plans operate exactly like that shared highway, while an app service environment acts as your isolated tunnel for single-tenant workloads. This matters because compliance frameworks like PCI-DSS require strict network segregation. If you skip isolation, noisy neighbors will cause latency spikes, and uncontrolled public endpoints expose your data to breaches. In this lesson, we will explore the fundamentals of app service environments and why they are critical for enterprise isolation. We will examine the architectural improvements in a SEV3, walk through provisioning steps using as web app create commands, and cover essential security practices for the AZ-305 exam. You must understand how to configure private endpoints and restrict NSG rules properly. If you misconfigure the internal load balancer mode, your applications will become unreachable from on-premises networks, causing immediate service outages during production rollouts. Let's define the core term precisely. An app service environment is a premium Azure App Service feature that deploys the entire platform runtime into your dedicated virtual network subnet. It provides a fully isolated environment for securely running containerized or code-based applications without sharing compute nodes with other tenants. This matters because multi-tenant shared plans cannot meet strict regulatory audit requirements. If you accidentally deploy standard workers into this subnet, the ICE provisioning will fail and corrupt your network routing tables. ICE offers 4 distinct capabilities that separate it from standard plans. First is network isolation through private endpoints and internal load balancers to keep all traffic off the public internet. Second is dedicated compute that eliminates noisy neighbor interference for consistent millisecond response times. Third is high-scale support handling over 50,000 requests per minute across microservices. Finally, security control integrates with NSGs and user-defined routes to enforce precise routing policies. Misconfiguring these routes will drop legitimate database connections entirely. It helps to compare standard app service with ICE side by side using concrete metrics. Standard plans are multi-tenant and share underlying infrastructure, whereas ICE is strictly single-tenant and dedicated. Network control differs significantly because standard plans assign public IPs by default, while ICE supports internal load balancer mode 0 for private access only. Scaling in ICE supports horizontal expansion across multiple worker pools, and the cost model includes a fixed stamp fee plus per worker pricing. Choosing the wrong plan will trigger unexpected monthly billing spikes. Visualize the actual data flow inside an ICE architecture step by step. A client request first hits a web application firewall or front door for DDoS protection. The traffic then passes through an internal load balancer that routes packets only to healthy instances within the dedicated subnet. From there, it reaches your web apps running in the isolated environment. This strict flow ensures that no public internet traffic ever touches your application directly. Bypassing the WAF will expose your endpoints to automated credential stuffing attacks. Now let's look at the procedure for provisioning an SEV3 correctly. We will follow a strict 3-step sequence to ensure a successful deployment. First, you must reserve an empty subnet in your VNet with at least 50 available IP addresses. Second, you deploy the environment using infrastructure as code like bicep templates. Third, you configure DNS and security controls to complete the setup. Skipping the IP reservation will cause provisioning failures and leave your network routing incomplete for production workloads. With the subnet reserved, we move to the second step, deploying the environment itself. You use a bicep template or ARM template to create the ICE resource, explicitly specifying the virtual network ID and subnet name in your parameters file. This step provisions the dedicated compute resources within your isolated network boundary. You must verify the subnet contains 0 existing resources before running as deployment create. Adding any other service to that subnet will permanently break the ICE networking stack. Finally, we complete the setup by configuring DNS and security controls. You must set up Azure private DNS zones to map your custom domains to the ICE private IP address using a records. Additionally, you implement NSG rules and WAF policies to control inbound traffic, ensuring only authorized requests reach your applications. You should enforce port 44.3 restrictions on all worker nodes. Leaving default open ports will allow unauthorized scanning and expose sensitive IPI endpoints to external threats. Here is the bicep code for deploying an SEV3 instance in practice. We define the resource with the kind set to a SEV3 and specify the location as EASTIS2. In the properties, we link the virtual network ID and the subnet name SNETAS subnet directly. We set the internal load balancing mode to internal to ensure private access, enable zone redundancy for high availability across 3 zones, and configure the worker size as medium with a count of 2 for scaling. Forgetting zone redundancy will cause downtime during regional maintenance windows. Best practices for ICE deployment focus heavily on network design and security architecture. Always plan your VNet subnets before deploying, because the ICE subnet must remain completely empty of other resources. Leverage Azure private DNS zones to map custom domains to the private IP address, ensuring internal services resolve correctly without public lookups. Implement layered security by placing an application gateway or front door in front of the ICE as a WAF, and use NSGs to restrict inbound traffic to only authorized IPs. Misplacing resources in the subnet will break all routing tables permanently. Remember this principle clearly. Isolation handles the infrastructure, but security remains your configuration responsibility. An ICE provides a dedicated environment, but you must still implement WAFs, NSGs, and robust identity management to secure the application layer effectively. You should enforce Azure Active Directory integration with conditional access policies for all admin portals. Failing to configure these controls will leave your isolated compute vulnerable to credential harvesting and unauthorized administrative actions during active attacks. Let's check your understanding with a quick certification question. What is a critical requirement for the subnet used by an SEV3, and what happens if you try to change the load balancer mode after deployment? The subnet must be completely empty with 0 other resources, and changing the load balancer mode after deployment is strictly not supported. You cannot switch from external to internal mode without deleting and recreating the environment. Attempting this will trigger immediate service failures and require a complete rollback of your network configuration. To recap, ICE provides physical and network isolation for enterprise workloads requiring strict compliance. Always prefer a SEV3 for new deployments due to its simplified architecture and native zone redundancy across 3 availability zones. Use internal load balancing and private DNS to keep applications off the public internet entirely. Finally, remember that ICE is not a set-and-forget solution. You must implement WAFs, NSGs, and use ISC for consistency. Neglecting these steps will cause compliance failures and expose your infrastructure to automated scanning attacks. For the AZ-305 exam, focus heavily on a SEV3 improvements over V1 and V2, specifically the removal of the management subnet requirement. Know exactly when to use ICE for compliance scenarios like PCID SSS or HIPAA. Understand the difference between internal mode 0 and external load balancer modes, and the importance of keeping the ICE subnet completely empty. Be prepared to identify best practices for network design and security integration using private endpoints. Misreading these exam questions will lead to selecting standard plans instead of isolated environments. Imagine you're moving a fragile package across town. You could buy a truck, maintain the engine, hire a driver, and stress about parking, or simply call a premium courier service that handles everything instantly. Azure Container Instances acts as that courier for your applications. It lets you run containers without managing any servers or virtual machines, giving you speed and simplicity in a serverless package while keeping costs predictable. We will master Azure Container Instances by exploring its core architecture and exam-critical concepts. First, we define the container group as the fundamental deployment unit. Then, we dive into configuring virtual networks for secure communication and mounting Azure files for persistent storage. We will review best practices to prevent resource exhaustion and conclude with a direct comparison against IKS to help you decide when to use serverless containers versus managed Kubernetes for your certification exam. The container group is the top-level resource in Azure container instances. It represents a collection of one or more containers that share a single lifecycle, a local loopback network, and mounted storage volumes. When you create a container group, all instances within it receive a unique IP address and DNS label, ensuring they communicate via localhost while being managed as a unified entity for scheduling and billing purposes. Use the as container create command to deploy your workload. Specify the resource group and name, set the image to mcr.microsoft.com/azuredocs/assi-helloworld, and assign 4 vCPUs with 7 GB of memory. Configure networking by setting the IP address type to public and providing a DNS label like myapsrv. This command creates the group instantly. Without the DNS label, external tools cannot resolve the endpoint reliably for testing. All containers within a group share a local host network, enabling communication via 127001 as if they ran on the same host. They also share mounted storage volumes, allowing seamless data exchange between instances. This architecture simplifies sidecar patterns significantly. For example, a log collector can read application logs directly from a shared volume without requiring complex network routing or external message brokers, reducing configuration overhead and potential failure points. Let's configure a container group for a production scenario by following 3 essential steps: defining images and resources, establishing secure networking, and mounting persistent storage. This sequence ensures your deployment remains isolated within the virtual network, maintains data integrity across restarts, and adheres to security best practices required for enterprise workloads on Azure container instances. Define the image and enforce strict resource limits to prevent runaway costs. In the YAML configuration, set the container name to app and use image engine X121. Specify CPU requests of 1 cores and memory of 1.5 GB. These values guarantee Azure schedules adequate compute. Omitting these fields defaults to minimal resources, which can cause your application to crash under load or trigger billing alerts due to unbounded consumption. Next, we configure networking by integrating the container group into an Azure virtual network. This integration enables secure communication with backend services, such as Azure SQL Database or Redis Cache, while keeping the workload isolated from the public internet. Proper subnet configuration is critical. Deploying to a shared subnet without network security groups can expose your application to unauthorized traffic and violate compliance requirements. Configure the networking profile by assigning the container group to a specific subnet, such as subnet ASI-01, and setting the IP address type to private. This restricts access to internal VNet peers only. You must also attach a network security group with deny-all rules for inbound traffic and allow list-specific ports like 8080 for application access, preventing accidental exposure of sensitive services to the broader network. Finally, we mount storage using Azure Files to ensure data persistence across container lifecycles. Since container instances are ephemeral and local storage is wiped upon restart, linking an Azure file share provides reliable, scalable storage. This step is essential for stateful applications. Without persistent storage, configuration files and logs will be lost during scaling events or updates, leading to data loss and service interruptions. In the YAML configuration, define a volume named data volume using the Azure file type. Specify the share name as appdata, the storage account stprodstorage01, and mount it to the container path mnt/data. This setup allows the application to read and write persistent data securely. Forgetting to provide the storage key or misspelling the share name will cause the deployment to fail with a mount error, halting your release. When designing infrastructure, choose ICI for simple, short-lived tasks or bursty workloads requiring minimal management overhead. Select IKS for complex, long-running microservices needing advanced orchestration, rolling updates, and deep integration with other Azure services. On the exam, recognize that ICI lacks node autoscaling and persistent local storage, making it unsuitable for stateful applications, whereas IKS provides full Kubernetes control plane capabilities for enterprise-grade deployments. Serverless containers allow you to focus entirely on code, while Azure handles the underlying infrastructure. ICI eliminates the need to manage virtual machines or cluster nodes, enabling rapid deployment and billing by the second based on vCPU and memory usage. This model reduces operational complexity significantly. However, remember that you still must define resource limits to prevent unexpected costs from runaway processes consuming your allocated quota. Test your knowledge. In a container group, how do containers communicate? The correct answer is via a shared local host network, allowing communication via 127.0.0.1. Containers share this loopback interface and mounted volumes, ensuring low-latency interaction without exposing endpoints to the public internet. This shared network property is fundamental to the ICI architecture and essential for implementing efficient sidecar patterns in your solutions. To recap, Azure Container Instances offer serverless compute without managing virtual machines. Container groups serve as the top-level resource, enabling shared networks and storage for grouped containers. You can integrate VNet connectivity for secure access and mount Azure files for persistent data storage. Use ICI for bursty workloads or batch processing, while reserving IKS for complex microservices requiring advanced orchestration and stateful capabilities. For the AZ-305 exam, focus on critical distinctions. ICI is serverless and billed by the second, with container groups as the top-level resource featuring shared lifecycle and network. ICI lacks persistent local storage. You must use Azure files for data retention. Select ICI for short-lived or bursty workloads, while choosing IKS for complex microservices requiring rolling updates and stateful management to meet enterprise requirements. Imagine managing a massive hotel chain where you care about guest satisfaction, not whether the heavy system works. That's exactly how Azure Kubernetes service operates. You focus on application code while Microsoft manages the control plane. For the exam, remember IKS abstracts the etcd database and IPI server, letting you deploy clusters like AZ-305 create without touching underlying infrastructure. This managed approach reduces operational overhead, ensuring your team ships features faster without getting bogged down in cluster maintenance. In this lesson, we'll break down the IKS architecture to prepare you for the AZ-305 exam. We'll examine how the control plane and node pools interact, compare Kubernetes versus Azure CNI networking models, walk through a CLI provisioning workflow using AZ-305 create, and cover best practices like system node pools for core DNS. Understanding these components helps you design resilient clusters and avoid common pitfalls during certification scenarios where precise configuration choices impact cost and security. Let's start with the core definition. Azure Kubernetes Service is a managed container orchestration service that simplifies deploying, managing, and operating Kubernetes on Azure by removing the need to manage the control plane yourself. Microsoft handles upgrades, patching, and health monitoring for the IPI server and etcd. This means you avoid downtime from manual updates, and can focus entirely on application logic, ensuring high availability without the operational burden of maintaining a complex control infrastructure. Here is how data flows through an IKS cluster. External requests hit the IPI server, which delegates scheduling decisions to the scheduler based on resource requests like CPU and memory limits. The controller manager ensures the desired state matches reality by reconciling pods with node capacity. This flow ultimately pushes workloads to your node pools where containers execute. Understanding this pipeline helps you troubleshoot scheduling failures and optimize resource quotas to prevent pod eviction during traffic spikes. Now let's get practical. We'll walk through the IKS provisioning workflow step by step using the Azure CLI. First, we need to set up foundational resources like a resource group and a virtual network with a dedicated subnet. Skipping this preparation causes deployment failures because IKS requires a pre-existing VNet subnet for pod IP assignment. Proper planning ensures your cluster integrates seamlessly with existing infrastructure and avoids networking conflicts that could block application traffic. First, you create a resource group using AZ-group create to hold your cluster resources in a specific region like East US. Then you define a virtual network with a dedicated subnet for IKS, ensuring the CIDR block is large enough to accommodate all pod IPs. This subnet will hold the pod IPs later on. If you size the subnet too small, you'll encounter IP exhaustion errors that prevent scaling your cluster, directly impacting your application's ability to handle increased load. Next, we need to identify that subnet so the cluster can use it. We query the subnet ID using AZ-network VNet subnet show to retrieve the unique resource identifier. This ID must be passed into the creation command to link the cluster to your VNet. Forgetting this step results in provisioning errors because IKS cannot assign pod IPs without a valid subnet reference. Verifying the ID ensures your networking configuration is correct before deployment begins. You query the subnet ID using the Azure CLI with a command like AZ-network VNet subnet show resource group myrg name my subnet query id.otsv. This returns the unique identifier for your subnet, which you store in a variable to use in the next step. Storing the ID correctly prevents typos in the cluster creation command. If the variable is empty or incorrect, the deployment fails immediately, wasting time and delaying your application release schedule. Finally, we deploy the IKS cluster itself using AZ-create. We specify the node count, such as setting node count 3 for high availability, select Azure CNI for networking with Network Plugin Azure, and link the subnet ID we just retrieved. This command orchestrates the entire cluster creation process. Choosing the wrong network plugin or insufficient nodes can lead to performance bottlenecks or single points of failure, jeopardizing your application's reliability during peak usage periods. You run the create command with 3 key settings: the node count for agents, the network plugin set to Azure for CNI support, and the subnet ID to wire up networking. SSH keys are generated automatically for access using Generate SSH keys. This setup ensures your cluster is fully integrated with your VNet, allowing pods to communicate directly with other services. If you skip SSH key generation or misconfigure the network plugin, you'll face connectivity issues that block developer access and disrupt CI/CD pipelines. Let's compare the 2 networking options you'll face on the exam. Kubernetes uses NAT and a separate pod network, requiring complex routing tables, while Azure CNI gives pods direct IPs from your VNet for native integration. For enterprise security and performance, CNI is usually the right choice because it supports network security groups directly on pod IPs. Choosing Kubernetes incorrectly can introduce latency and complicate troubleshooting, making it harder to enforce granular security policies across your infrastructure. One of the biggest advantages of IKS is that the control plane is fully managed and free. Microsoft handles upgrades, patching, and health monitoring for the IPI server and etcd database. This means 100% of the control plane complexity is offloaded to Azure, so you can focus on your workloads. You avoid downtime from manual updates and reduce operational costs significantly. If you self-manage the control plane, you risk configuration drift and security vulnerabilities that could compromise your entire cluster environment. Remember this principle for your design decisions. Network planning determines your scaling ceiling. If you don't size your subnet correctly, say using a 27-sider for a large cluster, you'll hit IP exhaustion and block deployments as pods run out of addresses. Plan your VNet CIDR blocks to accommodate current needs plus future growth, accounting for node IPs and pod IPs. Failing to calculate IP requirements leads to service disruptions where new applications cannot start, directly impacting business operations and user experience. Quick check. If you need every pod to have a direct IP address from your Azure VNet for granular security policies, which networking plugin should you choose? The answer is Azure CNI. This plugin assigns VNet IPs directly to pods, enabling network security groups to filter traffic at the pod level. Choosing Kubernetes would force you through NAT, preventing direct policy enforcement and complicating troubleshooting. Understanding this distinction is critical for passing exam questions about network security and compliance requirements. When designing your cluster, separate system workloads from application code to ensure stability. Use a system node pool for critical services like Core DNS and the Kubernetes dashboard, and a user node pool for your apps. This isolation prevents a noisy application from crashing essential cluster components by consuming all resources. You can also apply taints and tolerations to system pools to protect them. Failing to isolate workloads risks cascading failures where app issues disrupt DNS resolution or other infrastructure services. Let's recap what we've covered to solidify your knowledge. IKS gives you a managed control plane to reduce overhead, handling upgrades automatically. You choose between Kubernetes and CNI for networking, with CNI preferred for direct VNet integration. The provisioning workflow involves creating resources, getting subnet IDs via CLI, and deploying the cluster with AZ-305. Finally, separate node pools and proper sizing ensure stability. Mastering these steps helps you design secure, scalable clusters ready for production workloads. For the exam, focus on these key points for AZ-305. You must know how to provision a cluster with CNI networking using commands like AZ-305. Understand the difference between system and user node pools, including taints and tolerations for isolation. And remember that resource limits prevent noisy neighbor issues in your containers by capping CPU and memory usage. Mastering these concepts ensures you can answer scenario-based questions about cluster design, security, and cost optimization effectively during the certification test. Imagine your IKS cluster is a bustling metropolis where applications are skyscrapers demanding reliable infrastructure. If you build roads too narrow, network traffic grinds to a halt during scaling events, causing timeouts. If storage pipes leak, data vanishes when pods restart, leading to catastrophic failures. You must design networking and storage layers meticulously. Otherwise, your apps won't survive production loads or recover from node crashes without losing a single byte of critical information. We will master the design decisions that keep your IKS clusters running smoothly in production. First, We compare Azure CNI and Kubernetes network models while planning IP space to avoid exhaustion across subnets. Next, we configure ingress controllers like the Azure Gateway Ingress Controller for secure traffic management. Then, we dive into storage design, choosing between managed disks and Azure files based on access requirements. Finally, we cover critical best practices and CSI drivers you must know for the AZ-305 exam success. When creating an IKS cluster, the network plugin choice dictates performance and management overhead. Azure CNI assigns every pod a unique IP from your VNet subnet, enabling direct routing and high throughput, but requiring careful IP planning for node pools and pod scaling. Kubernetes uses a bridge model with NAT, simplifying initial setup, but adding latency for external connectivity. For production workloads requiring low latency and direct VNet integration, Azure CNI is the standard choice to avoid complex troubleshooting later. Let's walk through 3 essential steps to design a robust IKS infrastructure for certification scenarios. First, select the network model and configure the cluster with private endpoints to secure the IPI server against unauthorized access. We will see how to enforce this during creation using Azure CLI flags. This ensures your control plane remains isolated within your VNet, reducing attack surfaces and meeting compliance requirements for enterprise deployments where public exposure is strictly prohibited. This command creates a production-ready cluster in the central U.S. region using the Azure CNI plugin for direct networking. The Network Plugin Azure flag enables full VNet integration, while Enable Private Cluster ensures the IPI server is not exposed to the public internet, which is a critical security baseline. We also define Service Sitter 10.0.0.0.16 and DNS service prefix to prevent IP conflicts with existing virtual network resources, avoiding catastrophic routing failures during deployment. With the network model selected, we focus on securing and exposing traffic efficiently. You should avoid using load balancer services for every endpoint to reduce costs and attack surfaces. Instead, use an ingress controller like Nginx or IGIC to manage external access centrally via a single IP. We will configure an ingress resource that routes traffic based on hostnames, allowing you to serve multiple applications through one secure gateway, while enforcing TLS termination and path-based routing rules. This YAML defines an ingress resource named WebIngressAgic with the annotation Kubernetes, io/ingress class, Nginx. We add Apqua, ingress, Kubernetes, io/use private IP, true to bind the application gateway backend to a private IP, enhancing security within your VNet. The rules map host myapp. Example: com to service web service on port 80 using path type prefix, allowing you to route multiple microservices through a single entry point while validating requests against specific paths for precise traffic control. Finally, we provision storage to support stateful applications reliably. We define a storage class that tells IKS how to create disks or files dynamically using the CSI driver. By setting reclaim policy, retain, we ensure data persists even if a developer accidentally deletes a claim, preventing accidental data loss. We will configure a premium managed disk class with volume binding mode. Wait for first consumer to optimize placement and performance by binding storage only when a pod is scheduled on a specific node. This YAML block defines a storage class named Managed Premium Retain using the disk, CSI, Azure, COM provisioner with storage class name, Premium LRS. The reclaim policy, retain protects data from accidental deletion during cluster teardown. We use volume binding mode. Wait for first consumer to ensure the disk is created in the same availability zone as the pod claiming it, preventing cross-zone latency penalties. A PVC below requests 10 GB storage with read-write-once access, ensuring exclusive block-level access for a single-node database workload. Understanding the storage provisioning flow helps you troubleshoot issues effectively. When a pod requests storage, the CSI driver intercepts the PVC and communicates with the Azure API to provision the managed disk. The disk is then attached to the node hosting the pod via the instance ID. If using Azure files, the SMB share mounts directly onto the file system. Monitoring this flow via Container Insights metrics allows you to detect I/O latency spikes before they cause application timeouts or node pressure events. Choosing the right storage type depends on your access requirements and performance needs. Managed disks offer high IOPS, but support only read-write-once access, making them ideal for stateful databases like Postgres running on a single node. Azure files support read-write-many access across multiple pods, which is perfect for shared configuration files or content management systems requiring concurrent writes. Blob storage handles massive unstructured datasets, but requires specific mount tools like BlobFuse for POSIX-compliant access in containers. A CSI driver provides the standard interface Kubernetes uses to interact with external storage systems dynamically. It replaces older in-tree drivers, offering improved performance, security isolation, and feature parity for modern workloads. Always prefer CSI-based drivers like Disk, CSI, Azure, COM for production deployments to ensure long-term support and access to critical capabilities such as dynamic provisioning, snapshot management, and volume expansion without modifying core Kubernetes components or risking compatibility issues during upgrades. Remember this principle as you design your clusters. CSI is the mandatory standard for production storage. Using the container storage interface ensures your storage layer remains portable, performant, and fully supported by Microsoft. It allows you to abstract the underlying provider details and focus on application logic rather than storage plumbing. Adopting CSI drivers guarantees access to the latest features like encryption at rest and automated backup integration required for compliant enterprise environments. Let's check your understanding with a scenario. You have a stateful application requiring multiple pods to read and write to the same data store simultaneously across nodes. Which storage option should you choose? Managed disks only support read-write-once per node, blocking concurrent access. The correct answer is Azure Files, because it supports read-write-many access modes, enabling multiple pods mounted via SMB to share data concurrently without locking conflicts or performance degradation on the block layer. We have covered essential design patterns for IKS networking and storage. You learned to select network models like CNI versus Kubernetes and plan IP space carefully to avoid exhaustion. We configured ingress controllers to secure traffic with TLS termination and defined storage classes with CSI drivers for persistent data retention. Remember to use private clusters, enforce network policies for segmentation, and monitor storage latency via metrics to keep your infrastructure resilient against scaling events and failures during production operations. For the AZ-305 exam, focus on the trade-offs between CNI and Kubernetes, knowing CNI is preferred for performance and VNet integration. You will likely encounter scenarios requiring you to select the correct storage class for a given access mode requirement, like read-write-many. Pay attention to private cluster configurations and how they restrict IPI server accessibility to within your VNet only. Finally, remember that CSI drivers are the required standard for storage in modern Kubernetes deployments on Azure. Imagine you are running a pop-up shop at a busy festival. You simply set up your counter and serve customers as they arrive. This is exactly how serverless computing works in Azure. You bring the code, and Microsoft handles the underlying infrastructure through Azure Functions with consumption plan. If you misconfigure timeout or memory limits, deployments will fail under load. Mastering this model saves you from managing virtual machines while keeping costs predictable for the AZ-305 exam. We will explore the core concepts of Azure Functions today. You will see how triggers and bindings connect your code to data sources like service bus queues. We will walk through a practical queue processing example using the func-init command and cover essential best practices for the AZ-305 exam. Understanding these patterns prevents deployment failures when scaling to thousands of concurrent executions. Let's start with a precise definition for your certification review. Serverless does not mean there are no servers. It means you do not manage them. You abstract away the infrastructure layer entirely by using managed platforms like Azure Functions. This approach eliminates patching duties, but requires careful memory allocation to avoid throttling during peak traffic windows. Why do architects choose serverless for production workloads? First, you focus purely on business logic instead of VM administration. Second, the cost model is efficient because you only pay when code runs, typically measured in 100 millisecond increments. Third, it scales elastically based on event volume. Ignoring these traits often leads to over-provisioned resources and unexpected monthly bills. Azure Functions offers 3 distinct hosting plans for different architectural needs. The consumption plan scales automatically and handles bursty workloads efficiently. The premium plan pre-warms instances to reduce cold starts below 500 milliseconds, ideal for low-latency IPIs. The dedicated plan gives you manual control over resources using app service environment. Choosing incorrectly causes latency spikes or unnecessary compute charges. Let's look at a practical example using C# and Azure Functions. This order processor function uses the queueTrigger attribute to invoke automatically when a new message arrives in the order's queue. Inside the method, we log the processing event with a standard iLogger instance. Notice how clean the code remains without polling logic or background service management required for reliable delivery. Now let's design a robust serverless solution for production environments. We will follow 3 key best practices to ensure your functions are fully production-ready and exam-compliant. You must configure proper retry policies and set realistic timeout values around 60 seconds. Ignoring these settings frequently causes data loss during unexpected network interruptions or regional service degradation. First, keep functions strictly atomic during development. Each function should do one thing well without mixing responsibilities. If you have complex workflows, use durable functions to orchestrate them across multiple steps rather than cramming everything into a single method. Mixing concerns increases deployment failures and makes debugging nearly impossible during peak traffic periods. Next, we manage external connections properly across all deployments. This prevents socket exhaustion and ensures your application remains stable under heavy load. You should configure connection pooling limits around 500 sockets per worker instance. Failing to pool resources typically crashes the runtime when processing concurrent IPI requests simultaneously. To manage connections effectively, avoid creating new HTTP client or database instances inside the execution block. Instead, use a static singleton instance declared at class level. This reuses the underlying TCP connection and prevents resource exhaustion during rapid scaling events. Misplacing this pattern causes memory leaks and forces expensive restarts across your function app. Finally, ensure your logic is strictly idempotent before deployment. Serverless environments may retry executions due to network blips or timeout errors, so your code must handle duplicates safely. You should implement exponential backoff strategies and track unique transaction IDs. Skipping this step frequently results in duplicate charges or corrupted database records. For idempotency, check if an order has already been processed before charging a card or updating a database. Use unique identifiers to detect duplicates and skip redundant work immediately. You should query Cosmos DB with consistent read mode to verify state accurately. Failing to verify state causes financial discrepancies and violates compliance audit requirements. Remember this core principle for your certification review. Serverless is fundamentally about abstraction. You manage the application logic while Microsoft manages the underlying infrastructure and scaling policies. This division of labor reduces operational overhead, but requires strict adherence to platform limits. Ignoring these boundaries causes unexpected throttling and breaks automated deployment pipelines. Visualize how data flows through this specific architecture carefully. An event source triggers the function via a defined trigger attribute. The function executes your business logic within the allocated memory budget. Then, an output binding sends the result to a storage service like Cosmos DB or SQL. Misrouting bindings causes silent data loss and breaks downstream reporting tools. Quick check to test your knowledge right now. Which hosting plan is best for reducing cold starts in latency-sensitive applications? The answer is the premium plan, because it pre-warms instances and maintains minimum capacity. Choosing consumption instead causes unacceptable delays exceeding 2 seconds during initial request handling, breaking strict SLI requirements. We covered the fundamentals of Azure functions thoroughly today. You learned about triggers and bindings, built a queue processor using Service Bus, and applied best practices like atomic design and idempotency. Mastering these concepts prevents deployment failures during production rollouts. Always validate your configurations against official documentation before taking the certification exam. For the AZ-305 exam, focus on distinguishing between hosting plans and understanding when to use durable functions. Always assume your code might run multiple times due to retry policies. Design for failure by implementing idempotency checks and monitoring metrics through application insights. Skipping these steps causes incorrect answers on scenario-based questions. Imagine a conductor leading an orchestra where every musician plays perfectly, but has no sheet music or baton. Chaos ensues instantly. That is exactly what running complex serverless workflows without orchestration looks like. You get isolated functions firing randomly with no coordination. In Azure, standard functions are fantastic solo performers, but when you need to coordinate state across multiple steps, durable functions step in as the conductor. They manage the execution graph, track progress via the durable task framework, and ensure your orchestration trigger maintains consistency while orchestrating long-running processes like order processing or approval chains. Welcome back. In this session, we will master why durable functions are non-negotiable for scalable serverless architectures on the AZ-305 exam. We will define the core function types, specifically distinguishing orchestration trigger from activity trigger, and dive deep into the unique replay pattern that powers state management without external databases. You will review common orchestration patterns like chaining and fan-out fan-in. Then apply best practices to handle long-running workflows in logic apps or function apps, ensuring you can architect reliable solutions that pass certification requirements and avoid common pitfalls in production environments. Let's lock in the definition of an orchestrator function. This component acts as the deterministic engine driving your workflow logic, defining the exact execution order and conditional branches for all tasks. Crucially, orchestrators must remain lightweight and strictly deterministic because the durable functions framework replays this code multiple times during execution to rebuild state. If you introduce randomness or external I/O calls inside an orchestration trigger, the replay will produce inconsistent results, causing the workflow to crash or enter an infinite loop. Always keep orchestration logic pure to ensure reliable state reconstruction across every replay cycle. Compare this to what you already know. Standard Azure functions are stateless and event-driven, excelling at short, fire-and-forget tasks triggered by HTTP or queue messages. In contrast, durable functions introduce robust state management via the Durable Task Framework, supporting long-running processes that span hours or days. Use standard functions for simple request-response patterns, but switch to durable functions when you must track progress over time, manage distributed transactions across multiple services, or handle retry logic with specific delay intervals. This distinction is vital for architecting solutions that persist context without relying on external database writes for every step. Now let's examine the engine under the hood, the replay pattern. This mechanism allows durable functions to maintain complete workflow state without requiring a dedicated database for every step. The framework records every activity call and its result into an internal event log stored in Azure storage tables. Understanding this sequence is critical because the orchestrator rebuilds its local state by replaying these events from the beginning whenever execution suspends. If you misconfigure the event log or fail to await activities correctly, the replay will skip steps, leading to data corruption and failed audits in your serverless architecture. Here is the initial execution phase when you trigger the orchestrator function. The code runs normally from top to bottom, calling validate order and then process payment. During this run, the Durable Functions framework intercepts every activity call and records the result into the internal event log immediately. The function does not wait for external responses. It pushes through the entire code block rapidly. This rapid execution populates the event history with sequence numbers and status updates, preparing the state machine to handle suspensions later when long-running operations require waiting for downstream service responses. Next, we reach the suspension and replay phase triggered by a long-running activity. If an operation like process payment takes time, the orchestrator suspends execution immediately to free up resources. When the activity completes, the framework resumes the function and replays the code from the very beginning using the event log. It skips all completed activities based on recorded status and proceeds to the next step, rebuilding its local state instantly. This replay ensures consistency, allowing you to recover gracefully from failures without reprocessing completed steps or losing critical workflow context. This example demonstrates the critical replay logic in action. Notice the await statements controlling flow. When process payment is called, the orchestrator yields control and waits for the result. The framework records this wait event in the history. Later, when payment completes, the orchestrator replays from the start. It sees the log entry for process payment marked as completed, skips the actual call entirely, reads the stored result, and moves directly to checking the outcome and triggering the email notification function, ensuring idempotent behavior throughout the workflow execution. Beyond the core mechanism, durable functions support several powerful orchestration patterns for complex scenarios. Function chaining executes tasks sequentially in a strict order. Fan-out and fan-in run multiple activities in parallel to maximize speed, then aggregate results into a single output. Async HTTP/IP IS allow you to start long processes via start new and poll status using getStatus. Human interaction patterns pause workflows until a user responds via durable client. Mastering these patterns helps you design scalable solutions that handle concurrency, retries, and user delays effectively in production environments. Let's test your understanding with a critical exam trap. What happens if you use a non-deterministic operation, such as datetime.now, inside an orchestrator function? The replay will generate different timestamp values each time the code executes, causing the workflow to fail validation or behave unpredictably during state reconstruction. You must avoid any external dependencies that change between replays. Always keep orchestrators deterministic by using inputs provided in the function arguments rather than generating fresh data on the fly, ensuring consistent results across every replay cycle required for reliable execution. Remember this fundamental principle for certification success. Code is replayed, not just executed sequentially. Your orchestrator logic must be strictly idempotent and completely free of side effects, like sending emails or writing to storage during the orchestration phase. If a function produces a correct result on the first run, it must produce that exact same result every time the framework replays it from the event log. Violating this rule leads to duplicate actions, data inconsistency, and failed audits. So always separate your orchestration logic from side effect activities to maintain system integrity. To recap our key takeaways, durable functions enable stateful serverless workflows by combining orchestrators to define logic with activities that perform specific tasks. The replay pattern allows these functions to recover automatically from transient failures and manage long-running processes efficiently without external database dependencies. You can leverage patterns like chaining for sequential steps or fan-out for parallel processing to solve complex business problems reliably. Mastering these concepts ensures you can architect robust solutions that handle state, retries, and distributed transactions effectively in Azure environments. For the AZ-305 exam, prioritize determinism above all else. You will encounter questions requiring you to identify invalid code inside an orchestrator, such as random number generation, direct I/O operations, or calls to datetime.now. Also, know precisely when to recommend durable functions versus standard ones. Look for exam keywords like long-running, stateful, workflow coordination, or distributed transactions. Choosing the wrong pattern will cost you points, so always verify that your solution handles state persistence and replay constraints before selecting a serverless architecture for complex business processes. Imagine you are planning a delivery fleet for a growing business. You could buy massive trucks that waste fuel on small packages or tiny bikes that run cheaply but carry nothing. Choosing the wrong vehicle wastes money and slows customers. In cloud architecture, compute is that fleet, and selecting the right Azure service model separates lean operations from bloated disasters. Picking standard B-series VMs for simple scripts drains budgets through idle vCores, while misusing Azure functions for long processes triggers timeout errors. Master this framework to architect cost-efficient workloads. Today, we will master the framework that guides every compute decision on the AZ-305 exam. We start by breaking down the 4 pillars you must evaluate for any workload. Then we compare core service types side by side to see where they excel. Next, we walk through a step-by-step design process using real Terraform code snippets. Finally, we cover operational best practices and common pitfalls that trip up candidates. Understanding these trade-offs prevents costly misconfigurations during certification exams and ensures production environments run efficiently under heavy load. Every compute decision rests on 4 pillars. First is control versus abstraction. If you need kernel-level tuning or legacy OS dependencies, you grab high control with IaaS. Second is workload predictability. Steady traffic fits fixed instances, while spiky bursts demand aggressive scaling. Third is application architecture. Monoliths lift and shift easily, but microservices require orchestration. Fourth is operational overhead. Small teams should lean on managed services to avoid undifferentiated heavy lifting like patching. Running, as VM create size standard D2S v3, without checking core limits wastes budget and causes security gaps during performance reviews. This flow shows how the decision process moves in practice. You begin by defining workload requirements, capturing traffic patterns and dependencies. Next, you assess organizational constraints, looking at team skills and budget limits. Then you select the service model that fits both the workload and the constraints. Finally, you validate against security and compliance rules before deploying. Checking, as network NSG rule, outputs confirms proper ingress rules before deployment. Applying incorrect NSG configurations opens ports to the internet, causing audit failures during certification scenarios. This comparison grid highlights the trade-offs between the 3 main compute primitives. Virtual machines offer full control and predictable costs, but require significant operational overhead. Containers provide portability and rapid scaling, though they introduce complexity in orchestration. Serverless functions eliminate infrastructure management entirely and scale instantly, but you must watch for cold start latency and vendor lock-in. Monitoring, max scale, thresholds prevents unexpected egress fees during peak traffic windows. Choosing incorrectly causes throttling errors that degrade application responsiveness under load. We are going to walk through designing a compute solution step by step. This cumulative board will build the complete strategy as we go, so pay close attention to how each requirement shapes the final architecture. We will map requirements directly to Azure services like App Service and IKS. Using as App Service Plan creates SKU B1, sets baseline pricing, ensuring you can justify every architectural choice during the exam and prevents costly rework when migrating legacy workloads. In the first step, we analyze requirements. Consider a legacy Windows application requiring Net Framework v48 and local file system access. The code here defines a Linux virtual machine in Terraform. Notice the explicit IMI reference and instance type. This configuration demands that you manage the OS patches and updates yourself, which is exactly what the requirement analysis dictated. Running as VM run command invoke manually will fail if you forget to install required dependencies, causing deployment timeouts during certification labs. Now we move to the second step. With requirements defined, we select the service model. For an event-driven log processor that runs briefly and sporadically, we shift away from persistent infrastructure toward a function-based approach. We will configure Azure functions with consumption plan pricing to match variable traffic patterns. Setting min instances to 0 prevents cold start delays, ensuring your architecture scales automatically without manual intervention during peak exam scenarios. The code here implements a serverless function using Terraform. You define the function name and runtime environment. The provider handles all OS patching, so you focus entirely on the handler logic. This model perfectly matches our event-driven requirement, eliminating the need for a constantly running server. Running Func Azure Function App Publish verifies the bundle, ensuring configuration settings like website, run, from, package deploy correctly during timed certification assessments. Finally, we implement controls and orchestration. For a high-traffic microservice requiring rapid scaling, we deploy a containerized application managed by Kubernetes. This ensures portability and automated scaling logic. We will configure the horizontal pod autoscaler to target CPU usage below 70%. Reviewing, kubectl get pods, output verifies container health before scaling triggers. Applying incorrect autoscaling rules causes resource exhaustion during traffic spikes, leading to service degradation that examiners penalize heavily in performance scenarios. This Kubernetes manifest defines a deployment for a web API. You specify the replica count to handle load and define the container image source. The cluster manager handles the networking and scaling, allowing you to spin up instances in seconds rather than minutes. Using kubectl scale deployment API replicas ensures consistent throughput. Misconfiguring memory limits causes OOM-killed errors that crash your pods and fail practical exam tasks. A critical concept for the exam is stateless architecture. A stateless application stores no data locally on the compute instance. All state lives in external databases or storage services, allowing instances to be terminated and replaced instantly without data loss. You will configure Azure Cache for readies to hold session tokens. Setting max memory to 256 MB prevents memory leaks, ensuring cache invalidation errors stay away during scale-out events that examiners flag as architectural anti-patterns. Remember this principle as you design. Match the tool to the workload. Do not force a monolith into containers just for trendiness, and do not spin up heavy virtual machines for simple event triggers. The right choice balances technical fit with operational reality. Over-provisioning standard D-series VMs for background jobs wastes thousands of dollars monthly. Running as monitor autoscale sets thresholds, aligning compute capacity with actual throughput metrics to prevent budget overruns during audits. Let's check your understanding. You have a high-traffic REST API that scales from 10 to 10,000 requests per second in minutes. The architecture is microservices-based. Which compute model offers the best balance of rapid scaling and portability for this scenario? Azure Kubernetes Service provides the optimal answer here. Configuring CPU to 500M ensures stability, preventing manual scaling bottlenecks while avoiding execution timeout limits during complex request processing. We have covered the essential framework for compute decisions. You now know how to evaluate control versus abstraction, match workloads to service models, and implement robust orchestration strategies. Reviewing these patterns ensures you can quickly identify the correct service for exam scenarios. Applying as-create with 3-node pool replicas prevents cluster failures during practical assessments and solidifies your architectural reasoning. For the AZ-305 exam, focus on the trade-offs. You will often see scenarios where multiple services seem viable. Look for keywords like legacy dependencies to point to VMs or sporadic execution to point to serverless. Watch out for pitfalls like cold starts in serverless latency-sensitive apps, and remember that vendor lock-in is a real concern with heavy serverless reliance. Testing timeout 30 checks latency, preventing selection errors and saving critical time during timed certification exams. Picture a library where every book is delivered straight to your desk and collected the moment you finish reading. That is exactly how Azure Virtual Desktop operates for modern workforces. We centralize infrastructure in the cloud while delivering full Windows experiences across any device. Today, we will design a solution that perfectly balances performance with cost efficiency, ensuring your architecture scales reliably without breaking the bank. We will start by selecting host pool strategies tailored to your specific user groups. Next, We will configure FSLogic's profile management using a shared Azure Files premium storage account, which is absolutely critical for pooled environments. Then we will walk through a hands-on implementation, deploying resources via the AZ-VMSS command line. Finally, we will review exam-critical best practices and common misconfigurations that frequently trip candidates on certification day. Let us begin designing the core architecture by following a strict sequential workflow. First, we analyze user requirements to determine workload intensity and licensing tiers like Windows 10 Enterprise Multi-Session. You must map each department to specific compute needs before provisioning anything. Skipping this step often leads to over-provisioned host pools that waste budget or underpowered VMs that crash during peak business hours. When analyzing requirements, you must strictly categorize users by their actual workload patterns. Power users requiring local admin rights or legacy line-of-business applications demand dedicated host pools with at least 4 cores per virtual machine. Standard office workers can safely share resources across pooled VMs. This classification directly dictates your cost model and prevents expensive compute waste during quiet hours. Next, we configure the host pools and implement robust profile management solutions. You must explicitly select between personal or pooled types based on your prior analysis. Then you implement FSLogics to ensure user data seamlessly follows them across sessions. Forgetting this step causes critical configuration drift and forces users to rebuild their environments every single time they log in. Here is a practical bicep snippet defining a pooled host pool for multi-session workloads. We explicitly set the type parameter to pooled and configure the load balancer as breadth first. This configuration spreads active sessions evenly across all available virtual machines to maximize overall CPU utilization. Applying this template creates the reliable compute foundation required for enterprise-scale deployments without manual intervention. Finally, we apply strict scaling and security controls to protect the environment. We enable auto-scale rules that automatically adjust VM counts based on real-time demand, ensuring cost efficiency during off-hours. Security is strictly enforced using Azure ID conditional access policies that block connections from non-compliant devices. Neglecting these controls exposes your virtual desktops to unauthorized access and significant data breaches. This specific JSON profile configures auto-scale rules for your host pool. It defines a daily schedule that scales down to exactly 1 warm virtual machine during off hours and scales out based on active user count during business hours. Implementing this automation prevents expensive over-provisioning while maintaining strict performance thresholds that keep end users highly productive throughout the entire workday. Understanding load balancer types is absolutely crucial for maintaining optimal performance across your infrastructure. Breadth first distributes sessions evenly across all virtual machines, which is ideal for most workloads to balance CPU usage. Depth first fills one machine completely before starting another, which minimizes active VM counts and reduces licensing costs. Choosing the wrong algorithm inevitably causes resource contention or wasted compute capacity during peak hours. Storage performance directly impacts the daily user experience inside your virtual desktops. FSLogix requires low-latency storage to function correctly without introducing noticeable lag. Azure Files Premium SSD offers the best throughput for profile containers, ensuring fast logons and rapid file access even under heavy load. Selecting standard tiers introduces unacceptable latency that degrades application responsiveness and frustrates your workforce. Security must remain a foundational element of every architectural decision you make. Always pair IVD with Azure ID conditional access policies that require multi-factor authentication for all remote connections. You must explicitly block access from devices that fail compliance checks or lack endpoint protection. Ignoring these controls allows malicious actors to bypass perimeter defenses and compromise sensitive corporate data. Let us quickly check your understanding of core design principles. Which host pool type delivers the most cost-effective solution for standard office workers who regularly share applications? Consider how compute resources are allocated and how user density impacts overall licensing expenses. Selecting the wrong model will either waste budget on idle capacity or create severe performance bottlenecks during peak usage windows. FSLogix remains the industry standard for managing user profiles in pooled environments. It captures the entire profile inside a VHD container stored on a secure network file share. This architecture allows users to seamlessly resume their session from any available virtual machine in the pool. Without this tool, profiles remain locked locally to specific VMs, causing permanent data loss and constant configuration drift. We have thoroughly covered the essential aspects of designing reliable IVD solutions. You now know how to choose between personal and pooled host pools based on precise user requirements. We discussed FSLogix for centralized profile management and used Bicep templates to automate infrastructure provisioning. Finally, we reviewed scaling strategies and security controls that guarantee a resilient enterprise environment. For the AZ-305 exam, focus heavily on architectural design decisions rather than basic configuration steps. You will likely encounter scenarios requiring you to recommend a host pool type based on specific application dependencies or admin rights requirements. Remember that FSLogix is mandatory for pooled environments, and carefully calculate user density to select the correct load balancer algorithm for optimal performance. Imagine a bustling city where every building connects directly to every other building with its own private road. Traffic would be chaotic, and a single accident could paralyze the entire grid. Microservices architecture transforms that chaos into specialized villages managing their own traffic independently. On the AZ-305 exam, you will configure Azure IPI management to route traffic safely between these services. Mastering this pattern prevents cascading failures and ensures your production deployments scale predictably under heavy load. We will start by defining core microservices patterns that replace monolithic structures. Next, we dive into data sovereignty using the database per service pattern with Azure SQL and Cosmos DB. Then, we walk through resilient communication strategies, including circuit breakers in Azure Service Fabric and event-driven flows via Event Grid. Finally, we cover exam pitfalls like the distributed monolith anti-pattern. Mastering these topics prevents deployment bottlenecks and ensures you can architect scalable cloud solutions that pass certification objectives. Monolithic architectures bundle all components into a single deployable unit, which becomes a bottleneck as code bases grow beyond 50,000 lines. Microservices break this down into small, independent services organized around business capabilities like billing or inventory. This approach allows you to scale only the payment service using Azure App Service Autoscaling rather than spinning up the entire application. It enables technological flexibility and isolates failures, so one crashing module does not take down your production environment. In a monolith, data is shared via a single database, leading to tight coupling and deployment conflicts. The database per service pattern solves this by ensuring each service owns its private data store exclusively. Services interact strictly via REST APIs rather than querying each other's databases directly. This enforces data sovereignty and allows you to choose Postgres for relational orders or Cosmos DB for flexible product catalogs. Implementing this correctly prevents cross-service data leaks and simplifies independent scaling during peak traffic periods. This JSON configuration defines an Azure API management instance that acts as a single entry point for client requests. You can see two routes mapping specific paths to their respective backend services, each with a 30-second timeout value to prevent hanging connections. The rate-limiting section protects the services by capping requests per minute and setting a burst size of 10. Authentication is configured to validate JOT tokens from Microsoft Entra ID, which prevents unauthorized access and reduces server overload during traffic spikes. To implement resilient communication, we follow a sequential process starting with Azure App Service configuration. First, we configure timeouts to prevent thread exhaustion by setting the request timeout to exactly 10 seconds. This sets the foundation for safe retries and circuit breaking. Without proper timeout boundaries, your application threads will pool completely, causing cascading failures that crash your entire microservice cluster during unexpected latency spikes. This YAML config demonstrates a resilient HTTP client setup using the Azure SDK for Python. It sets a 5-second timeout to ensure requests do not hang indefinitely when downstream services are unresponsive. The retry policy uses exponential backoff with jitter to avoid thundering herds during recovery. A circuit breaker is defined with a failure threshold of 5 and a recovery timeout of 30 seconds, which prevents resource exhaustion and keeps your API endpoints responsive under heavy load. Next, we deploy circuit breakers to handle failures gracefully across your microservice mesh. This step builds on the timeout configuration by adding logic to trip the circuit when errors exceed a strict threshold. You will configure this using Azure Service Fabric or Kubernetes ingress controllers. Failing to implement this pattern causes repeated failed calls to drain connection pools and degrade overall system throughput during network partitioning events. This Python class implements the circuit breaker logic using the resilience library for Azure workloads. The call method first checks if the state is open to return a fallback immediately without executing the underlying function. It wraps the function in a try block to catch exceptions reliably. Upon failure, it increments the counter and trips the breaker to the open state once the threshold is reached, which stops cascading errors from propagating through your distributed architecture. Finally, we enable event retries to handle asynchronous communication failures across your cloud infrastructure. This completes the resilience strategy by ensuring messages are processed reliably or routed for manual inspection when errors persist. You will configure this behavior using Azure Event Grid topics and subscriptions. Skipping this step causes data loss and inconsistent state management when transient network issues interrupt your message broker pipelines during peak operational hours. This YAML config shows an event consumer setup with robust retry mechanisms for Azure functions. It listens for the order-created event and retries up to 5 times with a 10-second delay between attempts. Persistent failures are routed to a dead letter queue for manual inspection by your operations team. Idempotency keys are enabled to prevent duplicate processing on retries, which guarantees data consistency and prevents financial discrepancies in your payment workflows. This diagram illustrates the event-driven flow using Azure Service Bus as the central message broker. The order service publishes an event when a customer places an order through your web portal. The broker receives and routes this event to listening services via dedicated subscriptions. The inventory service processes stock updates, while the email service sends confirmations asynchronously. This decouples the producers from the consumers and prevents synchronous blocking during high-volume transaction periods. When designing communication, you must choose between synchronous REST calls and asynchronous event-driven patterns. Synchronous calls offer low latency but create tight coupling and can block threads during failures. Asynchronous communication provides loose coupling and better scalability through Azure Event Grid, though it introduces eventual consistency challenges. The table summarizes these trade-offs to help you decide the right approach for your use case, ensuring you avoid performance bottlenecks during peak application load. Decoupling is king within cloud architecture design. The primary goal of microservices is to allow services to evolve independently without triggering cascading failures across your infrastructure. You will verify this principle by isolating database schemas and enforcing strict IPI boundaries between components. Mastering this mindset prevents deployment conflicts and ensures your platform remains highly available even when individual modules require urgent hotfixes or major version upgrades. Let's check your understanding with a practical scenario. Which pattern ensures that each microservice owns its private data store and communicates via IPIs rather than sharing a database? You will encounter this exact question format on the certification exam when evaluating architectural trade-offs. Selecting the correct answer requires recognizing how loose coupling prevents cross-service dependencies and maintains data isolation across distributed cloud environments. We have covered the core microservices patterns and their practical benefits for cloud deployments. You learned about data sovereignty with the database per service pattern and implemented resilience using timeouts, circuit breakers, and event retries. We also explored the trade-offs between synchronous REST calls and asynchronous messaging via Azure Event Grid. Remember to avoid anti-patterns like the distributed monolith and focus on decoupling for long-term architectural success and exam readiness. For the AZ-305 exam, focus on recognizing microservices patterns and their specific trade-offs during scenario questions. You will likely encounter scenarios asking you to select the right pattern for scalability or resilience using Azure App Service or Kubernetes. Pay attention to keywords like data ownership, circuit breaker, and event-driven messaging. Also, be ready to identify anti-patterns such as tight coupling or shared databases through practical CLI configurations and architecture diagrams. Imagine a luxury hotel where guests never have to knock on individual room doors or search for the manager. Instead, they hand requests to a dedicated concierge who handles authentication and routes traffic smoothly. That is exactly what Azure IPI management does for your cloud ecosystem. It acts as the central facade between backend microservices and external consumers. For exam purposes, remember it abstracts complexity while enforcing standards. If you skip this layer, developers face inconsistent endpoints and security gaps. We will configure the gateway to validate tokens before requests ever touch production databases. We will explore the core architecture of IPIM and how it functions as a central facade. You will learn to implement security policies using XML configurations like validate JWT and apply rate limiting with rate limit by key. We will examine versioning strategies and multi-region deployments using Azure Front Door. Finally, we will cover VNet integration to secure backends and review production best practices. Understanding this roadmap matters because exam questions frequently test policy execution order and deployment configurations. Missing these details leads to failed certification attempts and insecure public endpoints in real environments. IPIM is built on 3 distinct planes that work together to manage your IPIs efficiently. The gateway handles the actual data plane traffic, receiving calls and routing them to backends while enforcing policies. The management plane lives in the Azure portal, where you define the IPI surface and configure settings using PowerShell or CLI commands. The developer portal provides a customizable website for consumers to discover IPIs and test endpoints directly. This architecture allows IPIM to handle millions of requests per second with sub-50 ms overhead. Confusing these planes during deployment causes routing failures and breaks your security boundaries. Policies are the defining feature of IPIM. They are a collection of XML statements executed sequentially on either the request or response lifecycle. You can apply these policies at 4 different scopes: global for the entire service, product for a group of IPIs, IPI for a specific set, or operation for individual endpoints. For example, applying rate limit at the product scope enforces limits across all associated IPIs simultaneously. This granularity allows you to enforce rules precisely where they are needed without affecting unrelated traffic. Misplacing a policy in the wrong lifecycle block causes silent failures and exposes your backends to uncontrolled load. Here is a practical policy configuration that combines JOT validation with rate limiting directly in the XML editor. In the inbound section, we first validate the JOT token from the authorization header against an OpenID configuration URL. If validation fails, it returns a 401 error immediately without reaching your backend. Next, we apply a rate limit of 10 calls per 60 seconds based on the subscription ID. This ensures only authorized users can access the IPI while preventing abuse through controlled throughput. Failing to set a proper timeout causes gateway hangs and exhausts your backend connection pools during traffic spikes. When designing your IPI surface, versioning is critical to avoid breaking changes for consumers. You can implement versioning using the path, a query string, or a custom header. Path-based versioning keeps URLs clean and restful by including the version number directly in the root, like v1 users. Query string versioning is useful when you cannot modify the URL structure easily. Header-based versioning allows for flexible client implementations without changing the endpoint format. Choosing the wrong strategy causes cache invalidation issues and forces consumers to rewrite integration code during minor updates. For high availability, you should deploy IPIM across multiple regions using the premium tier. Use Azure Traffic Manager or Azure Front Door to route client traffic to the nearest IPIM instance based on latency or health probes. IPIM provides built-in synchronization so that your policies and configurations remain consistent across all regions via the sync endpoint. This setup ensures that if one region goes down, traffic is automatically redirected to another healthy instance without interrupting service. Skipping regional redundancy causes prolonged downtime during maintenance windows and violates enterprise SLI requirements. To secure your backends, you should integrate IPIM with a virtual network using the private endpoint or inbound integration mode. This allows IPIM to communicate with internal services like app service private endpoints or internal load balancers without exposing them to the public internet. First, select the appropriate region and VNet for your IPIM instance. Next, configure the VNet integration settings to link the subnet where IPIM resides. Finally, verify connectivity by testing access to a backend service within the private network. Misconfiguring the peering rules blocks legitimate traffic and leaves your data plane completely unreachable. IPIM is the facade that protects your backend while presenting a unified face to the world. By centralizing traffic management, you can evolve your services independently without breaking consumer integrations. For certification success, remember that this principle translates directly to using set backend service to swap endpoints during deployments. Applying this mindset prevents cascading failures when updating microservices. Ignoring centralized control forces developers to patch individual applications and increases operational overhead across the entire platform, which examiners frequently penalize. Let's check your understanding of policy scopes. If you want to enforce a specific rate limit on all APIs within a product, which scope should you apply the policy to? The answer is product scope. This ensures that every API associated with that product inherits the rate-limiting rule, providing consistent control across the entire group. For example, applying rate limit at this level automatically blocks excess requests before they reach individual operations. Confusing product scope with global scope causes unintended throttling across unrelated services and breaks compliance logging. We have covered the essential design aspects of IPIM. It acts as a facade to decouple backends from public interfaces, using 3 core planes for management. Policies allow you to enforce security and traffic control without modifying backend code. Versioning strategies help manage changes gracefully, while multi-region deployments ensure high availability. Finally, VNet integration secures your infrastructure by keeping backends private. Mastering these components prevents deployment failures during certification exams and ensures your production environments maintain strict compliance with enterprise security standards. For the exam, focus on understanding policy execution order and scope hierarchy. Remember that inbound policies run before the backend call, while outbound policies run after. Practice configuring JOT validation and rate limiting in XML using the Azure CLI. Also, be prepared to identify when to use VNet integration for private backends and how multi-region setups improve availability. Always consider observability by integrating with application insights. Missing these details causes you to misinterpret scenario questions and overlook critical security configurations during troubleshooting exercises. Imagine a busy restaurant kitchen during the dinner rush. Orders pour in from waiters, but chefs can only cook at their own pace. Without a buffer, tickets get lost and customers leave angry. Azure Service Bus acts as that essential holding tray between your microservices. When you configure a queue with a 60-second lock duration and a maximum delivery count of 10, you guarantee that transient network blips never drop critical payment data. This prevents cascading failures when demand spikes during peak sales events. In this lesson, we will compare queues versus topics to master your communication models. We will explore the peak lock mechanism for reliability, dead letter queues for error handling, and how to implement idempotency in your consumers. You will learn to run as service bus topic, create commands, and configure subscription filters. Understanding these patterns prevents duplicate charge processing and ensures your distributed systems survive unexpected node failures during certification exams and production deployments. Service Bus offers 2 primary communication models for your architecture. Queues provide point-to-point messaging, where a single receiver processes each message exactly once. Topics support publish-subscribe patterns, allowing multiple subscribers to receive independent copies of the same event. You will configure these using as Service Bus queue create and set max delivery count values. Choosing incorrectly causes duplicate processing or dropped events, which directly impacts your exam score and production system reliability under heavy load. Let's compare these models side by side for your architecture design. Queues follow a point-to-point model where each message is consumed by exactly one receiver, making them ideal for load-leveling tasks like order processing. Topics use publish-subscribe, where every subscriber gets a copy of the message, perfect for event distribution across inventory and billing systems. Misconfiguring competing consumer groups causes race conditions that corrupt database records during peak traffic hours. Visualize the data flow in a publish-subscribe scenario using Azure Service Bus. A sender publishes a message to the topic resource. The topic then distributes copies of that message to each subscription attached to it. Each subscription applies its own SQL filters and routes the relevant messages to its specific subscribers. This separation ensures different microservices react independently without tight coupling, preventing cascading failures when one downstream API experiences latency spikes. Now let's design a reliable receiver for your messaging pipeline. First, lock the message immediately using pclock mode to prevent duplicate processing while you execute your business logic. You must set the lock duration to exactly 60 seconds to match typical API call timeouts. Failing to acquire this lock guarantees that background worker threads will accidentally process the same transaction twice, corrupting your financial ledger and failing the certification scenario. We create a client using the fully qualified namespace connection string, then instantiate a sender specifically for the order's topic resource. Next, we define a message with a JSON body and an application property explicitly set to premium tier. Finally, we send the message asynchronously using send-to-sync to the broker endpoint. Skipping this asynchronous pattern blocks your main thread and causes timeout exceptions that crash your web server during high-throughput testing. Next, execute your business logic and validate the incoming payload against your strict schema requirements. You should explicitly check for null values and verify that numeric fields fall within acceptable ranges before committing changes to storage. Ignoring these validation steps allows malformed data to propagate through your pipeline, causing downstream database constraints to fail and triggering unexpected service restarts during critical production windows. The processor listens continuously to the subscription endpoint and handles incoming messages as they arrive. Inside the handler, we extract the JSON body and log the transaction identifier for audit trails. Crucially, we call complete message async only after successful processing to remove the item from the queue, ensuring the lock is released safely. Calling this method too early causes duplicate execution when network timeouts force the broker to redeliver the payload. Finally, complete the message to permanently remove it from the queue or abandon it immediately if an error occurs during processing. This pattern ensures at least once delivery without permanent data loss across your distributed components. You must configure the max delivery count property to exactly 10 attempts before routing failed payloads to the dead letter queue. Forgetting this threshold causes infinite retry loops that exhaust your compute resources and crash your application pool. A dead letter queue is a specialized sub-queue that captures messages failing to process after a configured number of delivery attempts. It acts as a mandatory safety net for manual inspection, allowing you to analyze malformed JSON payloads or repeated authentication failures without blocking the main processing flow. You will configure these via as-service-bus queue create with dead lettering enabled. Ignoring this queue causes silent data corruption that violates compliance audit requirements during certification assessments. Because Service Bus guarantees at least once delivery, you must design consumers to handle duplicate messages gracefully by checking unique message IDs against your database. Additionally, use sessions to enforce strict ordering for related messages, ensuring they are processed sequentially by a single receiver with a specific session ID. This combination of idempotency and sessions prevents race conditions that overwrite critical financial records during high-concurrency transaction processing scenarios. Decoupling your services with reliable messaging is the absolute foundation of resilient cloud architectures. It transforms brittle direct API integrations into scalable, event-driven systems that can withstand sudden node failure and massive traffic spikes. You will apply this principle when configuring Azure Service Bus namespaces with standard tier capacity units. Neglecting decoupling causes tight coupling that triggers cascading outages across your entire subscription during peak holiday shopping periods. What happens if a receiver crashes before completing a message? The lock expires after the configured duration, and the message immediately becomes available for another receiver to process. This mechanism ensures no data is lost, even during unexpected virtual machine reboots or network partition events. You will encounter this exact scenario on certification exams when evaluating failover strategies for distributed order processing pipelines. We have covered queues versus topics for communication models across different architectural patterns. We explored the P-clock mechanism for reliability and dead-letter queues for systematic error handling. Finally, we discussed idempotency and sessions to ensure strict data integrity and ordering in your consumer applications. Mastering these configurations prevents duplicate processing errors that frequently appear on cloud architecture certification exams and disrupt production workloads. For the exam, focus on choosing between queues and topics based strictly on the scenario requirements. Remember that P-clock ensures at least once delivery, so explicit idempotency checks are absolutely required. Dead-letter queues are essential for isolating corrupted payloads during error handling. Always consider sessions when strict ordering matters across related transactions. Practicing these patterns prevents costly misconfigurations that fail your certification assessment and break production pipelines. Imagine a busy newsroom where reporters send updates to editors via a smart dispatch system. The reporters do not need to know which editor reads the story, they just publish it, and the right person receives it instantly. This is exactly how event-driven architecture operates in the cloud, with Azure Event Grid acting as your intelligent routing backbone. Mastering this pattern prevents tight coupling, ensures your microservices scale independently, and keeps production systems responsive under heavy load. In this lesson, we will explore the core concepts of event-driven architecture, walk through implementing a real event flow with code, review critical best practices to avoid common pitfalls, and finish with key exam tips for the AZ-305 certification. You will learn how to configure topics using the Azure CLI, manage subscription filters, and troubleshoot delivery failures before they impact your production workloads. Let us define our star player, Azure Event Grid. It is a fully managed, intelligent event routing service that operates across regions with sub-millisecond latency. You will use it to manage the routing of all events from any source to any destination using a strict publisher-subscriber model. Understanding its core components prevents misconfigurations that cause dropped messages or excessive IPI call charges during peak traffic. Why move away from traditional request-response models? Because they often lead to tight coupling where services wait on each other. Event-driven architecture solves this by offering decoupling, so producers do not need to know their consumers. It boosts scalability since you can add subscribers without touching the producer, and ensures resilience through buffering and retries, which directly prevents cascading failures during sudden traffic spikes. Let us visualize a practical pipeline. When a user uploads a profile picture to blob storage, this triggers an object-created event. Event Grid receives this payload and fans it out to 3 independent handlers. One generates a thumbnail using Azure Functions, another updates a Cosmos DB record, and a third sends a notification email via SendGrid. All operations happen asynchronously without blocking the main thread. Now let us look at how you implement this. We will use a cumulative reveal to walk through the 3 essential steps of setting up an event flow. First, defining the topic. Second, creating the subscription. And third, writing the handler logic. Mastering this sequence ensures you deploy consistent schemas and avoid routing errors that break downstream consumer applications. Here is how you publish a custom event using the Azure SDK for C. First, we create an Event Grid Publisher client using the topic endpoint and a credential. Then, we construct an Event Grid event with the subject, type, and data payload. Finally, we call sendEventAsync to push that event into the grid, which guarantees delivery tracking and prevents lost notifications during high-throughput scenarios. With the topic defined, we move to the second step, creating the subscription. This is where you tell Event Grid which destinations should receive events and apply any filters to narrow down the stream. You will typically configure endpoint URLs for webhooks or function apps, ensuring that only relevant payloads trigger downstream processing and keep your compute costs predictable. For the handler side, Azure Functions is the most common choice. In this code, we use the Event Grid Trigger attribute to automatically invoke the function when an event arrives. Inside the method, we extract the data from the Event Grid event object and process it using standard logging. Configuring retry policies correctly prevents duplicate processing and keeps your execution timeouts within acceptable limits. The final step is handling the event logic itself. This involves ensuring your code is robust, idempotent to handle duplicates, and secure by using proper authentication mechanisms like SIS tokens or Azure ID. Implementing these safeguards protects sensitive data from unauthorized access and ensures that failed operations do not corrupt your underlying storage accounts during routine maintenance windows. In a real production scenario, your handler must be idempotent. Since Event Grid guarantees at least once delivery, you might receive the same event twice. Your logic should check if the work is already done before proceeding, preventing duplicate database entries or side effects. This approach maintains data integrity and avoids costly reconciliation steps when network timeouts trigger automatic retries. When designing your solution, it is crucial to choose the right tool. Event Grid is best for reactive scenarios where you need high throughput and low latency. In contrast, Service Bus is better for transactional messaging requiring ordering and sessions, while Event Hubs handles massive telemetry streams. Selecting the correct service prevents performance bottlenecks and keeps your monthly cloud spend aligned with actual workload demands. Here is a pro tip for your design decisions. Use Event Grid for reactive scenarios where you need to react immediately when something happens. Reserve Service Bus for complex queuing logic where message ordering and sessions are critical. Applying this rule correctly ensures your architecture meets strict compliance requirements while avoiding unnecessary latency during peak operational hours. Let us check your understanding. If you are designing a system that requires guaranteed message ordering and session tracking for financial transactions, which service would be the better choice? Event Grid or Service Bus? The correct answer is Service Bus because only it supports first-in first-out sequencing and explicit session states, which are mandatory for audit trails and regulatory compliance. To wrap up, remember that Azure Event Grid enables decoupled, scalable architectures through its PubSub model. Always implement idempotent handlers to handle at least once delivery, use dead lettering for failed events, and choose the right tool for your specific throughput and ordering needs. Mastering these patterns ensures your solutions pass architecture reviews and maintain high availability during unexpected traffic surges. For the AZ-305 exam, focus on recognizing when to use Event Grid versus other messaging services. Know the core components like topics and subscriptions, and be prepared to identify best practices, such as using subject filtering and configuring dead letter storage for operational health. Understanding these concepts will help you confidently answer scenario-based questions about scalable cloud architectures. Imagine a massive highway system where millions of cars enter from different on-ramps every second. If the road narrows or traffic lights fail, the entire network grinds to a halt. In cloud architecture, we need that same high-speed reliability for data. Azure Event Hubs serves as that critical infrastructure, acting as the front door for massive event streams while keeping your downstream systems safe and decoupled. Without proper partitioning, your ingestion pipeline will drop messages during peak load, causing costly reporting gaps in production environments. In this lesson, we will explore what Event Hubs is and why it matters for streaming architectures. We will look at the core architecture, specifically partitions and consumer groups. Then we will build a producer and consumer using the SDK. Finally, we will cover best practices to ensure your solution is secure and performant. Run as Event Hubs namespace, create with exactly 20 throughput units during provisioning. Skipping this planning phase causes severe bottlenecks when IoT devices suddenly spike their telemetry rates. Azure Event Hubs is a fully managed, real-time data ingestion service. It is designed to ingest millions of events per second from various sources like IoT devices, clickstream data, or application logs. Think of it as a highly scalable message broker that decouples your data producers from the consumers, allowing them to scale independently without affecting each other. If you misconfigure the retention period to exactly 7 days, older telemetry will permanently vanish, making historical compliance audits impossible and violating strict regulatory data requirements. To design effective solutions, you must understand the core components. First, event producers are any entities sending data, such as mobile apps or sensors. Second, partitions are critical. An event hub is divided into partitions, each acting as a separate stream for parallel processing. Third, consumer groups provide independent views of the same event stream, allowing multiple applications to process data simultaneously. A key stat to remember is that one throughput unit provides exactly 1 megabytes of ingress per second. Underestimating partition counts locks your ingestion speed at 2 megabytes per second. Here is how the data flows through the system. Producers send events to the event hub, which distributes them across partitions based on a partition key or round-robin assignment. Multiple consumer groups can then read from these partitions independently. This architecture ensures that different downstream services, like a real-time dashboard and an archival database, can both consume the same stream without interfering with each other. Failing to specify a partition key will cause uneven data skew, leaving some storage nodes overloaded while others sit completely idle during peak traffic. When planning capacity, you need to understand the difference between throughput units and processing units. TUs are used in the standard tier and measure ingress and egress throughput along with message counts. PUs are used in the premium tier for more predictable performance and higher isolation. If you need burst capabilities or dedicated resources, the premium tier with PUs is your choice. Mixing up these metrics will lead you to select the wrong SKU, causing unexpected throttling when your application exceeds 50,000 messages per second. Let's walk through implementing Event Hubs step by step. First, we will connect to the hub using the SDK and configure the connection string. Second, we will send data in batches to maximize throughput and reduce overhead. Third, we will process events with a checkpointing mechanism to ensure reliability. You must explicitly set the batch size parameter to at least 100 items before calling the send method. Otherwise, your network calls will generate excessive latency and quickly exhaust your allocated throughput budget. Here is the code for the producer. We create an Event Hub producer client using a connection string and the hub name. Then we create a batch of events, adding telemetry data points to the batch. Finally, we send the entire batch asynchronously. This batching approach significantly reduces network overhead compared to sending individual messages. If you forget to dispose the client object during shutdown, your background threads will leak memory and eventually crash the hosting virtual machine after several hours of continuous operation. Now we move to the next phase of implementation. First, we connect to the hub using the SDK and configure the connection string. Second, we send data in batches to maximize throughput and reduce overhead. You must explicitly configure the checkpointing blob container path before starting the processor loop, otherwise the system will lose track of processed offsets. This oversight causes duplicate event processing during automatic failovers, which breaks idempotency requirements for financial transaction records. This code demonstrates the consumer side using the event processor client. We set up a blob container for checkpointing storage, which tracks our progress. The processor listens for events and updates the checkpoint after processing each batch. This ensures that if the application restarts, it resumes from the last processed position rather than rereading everything. Failing to implement this pattern will force your downstream analytics pipeline to reprocess terabytes of historical data every time a worker node crashes or scales up. Finally, we complete the implementation. First, we connect to the hub using the SDK and configure the connection string. Second, we send data in batches to maximize throughput and reduce overhead. Third, we process events with a checkpointing mechanism to ensure reliability. You must always attach Azure Monitor alerts to track your egress metrics, because unmonitored data export costs can quickly spiral into unexpected monthly bills that exceed your entire cloud budget allocation. Let's check your understanding. What is the consequence of not implementing checkpointing in your Event Hub's consumer? Think about what happens when the application restarts. The correct answer is that you will lose your read offset entirely, forcing the system to replay every single message from the retention window. On the exam, this concept directly tests your knowledge of exactly how many days standard retention lasts before data becomes permanently purged from the underlying storage infrastructure. Remember this key principle: partitions are permanent. You cannot change the number of partitions after creation. Plan your partition strategy carefully based on your expected peak throughput to avoid bottlenecks later. Exam questions frequently trap candidates who assume they can scale partition counts dynamically, which actually violates the core design constraint and forces you to provision an entirely new Event Hub namespace instead. To recap, Event Hubs is the backbone of real-time streaming in Azure, offering high throughput and durability. Partitions are permanent, so plan your strategy up front. Decouple producers and consumers to handle traffic spikes safely. Checkpointing is mandatory for reliability, and always use managed identities to secure your data streams. Skipping these architectural safeguards will inevitably cause cascading failures during load testing, leaving your production environment completely unable to process incoming telemetry events. For the AZ-305 exam, focus on these key points. Event Hubs is used for high-volume ingestion, not low-latency messaging like Service Bus. Always choose the correct partition count during creation. Use consumer groups for independent processing views, and remember to use managed identities instead of hard-coding connection strings. Misidentifying the service will cost you immediate points on scenario-based questions that explicitly mention microsecond latency, requirements versus massive telemetry ingestion patterns. Imagine a busy restaurant kitchen where the waiter takes an order and instantly routes it to the chef, then notifies the delivery driver without writing a single note. Azure Logic Apps acts as that intelligent dispatcher for your cloud infrastructure. It automates tasks and workflows across SaaS platforms, databases, and custom APIs, allowing you to integrate systems with minimal code while Azure handles the scaling and server management behind the scenes. In this lesson, we explore core concepts making Logic Apps a powerful integration tool. We'll break down workflow anatomy, examining triggers like when HTTP request is received, and actions such as create blob. Then we'll walk through designing robust flows using CodeView to ensure reliability. Finally, we'll cover key takeaways and exam tips for AZ-305, focusing on cost optimization and security configurations that frequently appear in scenario-based questions requiring precise architectural decisions. Azure Logic Apps is a cloud-based PaaS designed for automation. It operates on a serverless model. You never manage VMs, as Azure automatically scales the execution environment based on demand. This drastically reduces boilerplate code and accelerates development time. With over 1,000 pre-built connectors, you can bridge services like SQL Database and SaaS apps like Salesforce. Understanding this PaaS boundary is crucial for exams, as misconfiguring infrastructure management leads to licensing errors or performance bottlenecks in production. At the heart of Logic Apps lies the workflow, a sequence of automated steps defining integration behavior. It starts with a trigger, such as when a file is created, followed by actions like send an email that perform the work. You must distinguish triggers from actions because triggers define the entry point and schema, while actions execute logic. Confusing these causes deployment failures in ARM templates and makes debugging runtime errors significantly harder during certification scenarios. Let's visualize data flow through a Logic app. An event like an HTTP post request triggers the workflow, passing a payload to the first action. Actions execute sequentially. For example, parse JSON transforms input before insert row writes to SQL Server. Connectors act as managed wrappers, enabling secure communication via OAuth or IPI keys. Data must flow correctly between steps. Failing to map dynamic content results in null values and broken downstream integrations that fail silently in production. Now let's design a robust Logic app workflow step by step. First, we define the trigger starting the process and establishing the input schema. For an HTTP trigger, specify post, methods, and validate required fields like ordered. This schema validation prevents malformed data from entering your flow. Defining the correct schema upfront ensures type safety and avoids runtime errors when downstream actions expect specific data structures for processing. Here is the JSON definition for an HTTP trigger. Notice the triggers block specifying the method and a schema validating fields like ordered. This schema ensures data integrity before execution. The kind property must be set to workflow for standard flows. If you omit kind, the runtime may misinterpret the trigger type, causing deployment failures in bicep scripts and preventing the workflow from responding to IPI calls correctly. Next, we add actions processing data after the trigger fires. Actions such as transform JSON or get row execute sequentially. We configure each action to reference dynamic content from previous outputs, creating a dependency chain. You must verify connection references exist. Missing connections cause deployment errors. Proper chaining ensures data propagates correctly, preventing orphaned records and ensuring downstream services receive accurate, formatted information for processing. This JSON shows an email action block. The run-after property controls flow. Empty means immediate execution after the trigger. We use host to reference a connection managing credentials securely via Azure Key Vault integration. The body constructs messages using dynamic content like ordered. Hard-coding credentials here violates security best practices and risks exposure in source control. Using connections ensures compliance, and prevents credential rotation, failures across environments. Finally, we secure the workflow using managed identities to authenticate to resources like SQL database without storing passwords. We wrap actions in scopes to handle errors gracefully. For example, a scope can catch exceptions from a create user action and trigger a fallback notification. This prevents infinite loops caused by recursive triggers. Proper error handling ensures audit trails remain intact and stops cascading failures that could exhaust your execution budget rapidly. This bicep snippet configures a logic app with a managed identity. The identity block assigns a system-assigned identity, allowing authentication to SQL database via our back roles like SQL Reader. This eliminates password storage in parameters files. You must assign the identity to the resource's role definition explicitly. Failing to do so results in access, denied errors during runtime, breaking integrations, and requiring manual intervention to restore connectivity between services. Choose the right plan based on workload characteristics. Consumption offers pay-per-execution pricing, ideal for sporadic tasks under 10 minutes duration. Standard runs on a dedicated app service plan, enabling VNet integration for accessing on-premises SQL Server via private endpoints. Select Standard when you need fixed resources or specific networking controls. Miselecting plans causes throttling errors in high-volume scenarios or unnecessary costs for predictable workloads requiring guaranteed performance guarantees. Remember, logic apps excel at orchestration and workflow management across services. For heavy data transformation exceeding 10 minutes or complex computations, offload logic to Azure functions. This separation keeps workflows maintainable and cost-effective. Combining heavy logic causes execution timeouts and increases costs due to longer runtimes. Architects must recognize this boundary to optimize performance and ensure your integration patterns remain scalable and efficient for exam scenarios. Let's check your understanding. What is a common pitfall when using file-based triggers in logic apps? Consider the scenario where a workflow creates a file in the same folder it monitors. This can lead to an infinite execution loop, causing unexpected costs and performance issues. Always ensure your actions do not trigger the same event they are listening for. This recursive behavior wastes execution minutes and can trigger subscription-level throttling limits. We covered Azure Logic Apps Essentials. You understand workflows using triggers like when HTTP request and actions for automation. We explored JSON definitions for CI/CD pipelines and best practices, including managed identities for secure authentication. Finally, we compared consumption and standard plans to select the right architecture. Mastering these concepts ensures you can design scalable integrations, manage costs effectively, and pass certification questions requiring precise architectural justification and code analysis. For AZ-305, identify when to use logic apps versus Azure functions based on orchestration needs. Secure workflows using managed identities over SIS keys for better governance. Understand consumption versus standard plans regarding VNet integration and private endpoints. Recognize pitfalls like infinite loops from recursive triggers and throttling limits per subscription. Focus on cost optimization scenarios and be prepared to justify architectural choices involving hybrid connections and security configurations in exam questions. Imagine you are running a live news ticker. If you had to ask every single reader individually for the latest headline, your day would be over before you finished the morning paper. Traditional web apps work exactly like that by waiting for requests, but modern applications need to push updates instantly to thousands of users simultaneously. We will explore how Azure SignalR service and PubSub solve this challenge by offloading complex connection management so you can focus on your business logic. You will learn to configure the AZ-SignalR create command with a standard S1 tier and 256 connections, ensuring your architecture scales efficiently without dropping live updates. Here is what we will cover to master real-time solutions on Azure. We start by understanding the core problem with traditional HTTP and why persistent connections are difficult to manage at scale. Then we dive into Azure SignalR service, looking at its .NET integration and code patterns. Next, we examine Web PubSub for language-agnostic scenarios. Finally, we review best practices like serverless modes and common pitfalls to avoid during your design. You will learn to deploy the AZ web app create command with a Linux container and configure scaling rules that prevent memory leaks during heavy traffic. Let's figure out why real-time communication flips the script on traditional web development. In standard HTTP, the client asks for data and waits. This is request response. Real-time pushes data from the server to the client instantly. If you tried to build WebSockets manually on your own servers, you would face massive scalability issues. Managing thousands of persistent connections consumes heavy CPU and memory, and load balancing becomes a nightmare due to sticky session requirements. Azure services abstract this complexity entirely, preventing application crashes when traffic spikes exceed your baseline capacity. First up is Azure SignalR service. This managed offering powers real-time web applications built on the ASP.NET Core SignalR library. It acts as a bridge between your application server and your clients. Your server sends messages to the service, which then handles the heavy lifting of broadcasting those messages to all connected clients. This is the preferred choice if you are already in the .NET ecosystem, as it provides high-level abstractions for groups and users out of the box. Misconfiguring the connection string will immediately break authentication flows across your endpoints. Let's look at how this works in practice with an e-commerce notification system. On the server side, we define a hub class that inherits from the base hub type. This hub contains a method to send updates to all connected clients using clients.all. In your configuration, you register SignalR and add the Azure backend using the builder pattern. On the client side, you establish a connection to the hub URL and listen for specific events like receiving an order update, logging the message when it arrives. Skipping reconnection logic causes dropped messages during network blips. Now we need to decide which service fits your architecture. Azure SignalR service uses the SignalR protocol and is tightly integrated with .NET, making it ideal for chat, dashboards, and collaboration tools where you want high-level abstractions. In contrast, Web PubSub relies on standard WebSockets and is language agnostic. It offers more control over the protocol and is better suited for IoT feeds, live gaming, or scenarios involving multiple programming languages like Python or Go. Choosing the wrong protocol will lock your team into a single backend framework permanently, violating exam requirements for multi-language support. Visualizing the data flow helps clarify why we use these services. The process starts with your application server sending a message to the Azure service. The service then acts as the publisher, distributing that message to all connected clients simultaneously. This decouples your backend from the connection lifecycle. Whether you are using SignalR or Web PubSub, the pattern remains consistent. Your server talks to the managed service, and the service handles the fan-out to the end users. Misrouting the traffic through a standard load balancer will break persistent session tracking entirely. Moving on to Azure Web PubSub, which takes a different approach. Unlike SignalR, which is tied to its specific protocol, Web PubSub is built on the standard WebSocket protocol. This makes it highly efficient for event-driven architectures and allows you to use custom protocols if needed. It uses a publish-subscribe model, making it ideal for sending messages to millions of clients without being locked into a specific framework. If your stack includes Python or Go, this is likely your best option. Forgetting to enable cores will immediately block cross-origin WebSocket handshakes from your front end. Here is a practical example of PubSub in action using Python for a live stock ticker. You initialize the service client using your connection string and specify a hub name, such as stock ticker. To broadcast data, you call sendAll on the service instance with your message payload. This approach allows you to push market data to thousands of users instantly, demonstrating how PubSub handles large-scale fan-out without requiring .NET. Skipping proper error handling will cause silent failures when the underlying WebSocket connection drops unexpectedly during peak trading hours. Let's work through the best practices for designing these solutions. First, use groups for scoping instead of broadcasting to everyone. This ensures users only receive relevant data. Second, implement serverless mode using Azure functions to scale to 0 when idle, which significantly reduces costs. Third, always monitor connection limits based on your service tier to prevent degradation during traffic spikes. Configuring the SignalR update command incorrectly will immediately break group routing and cause duplicate notifications across all connected devices, wasting bandwidth and confusing end users. Remember this key principle. Use these services strictly as a communication layer, not as a data store. Keep your business logic in your backend services and use SignalR or PubSub only for real-time delivery. This separation of concerns ensures your architecture remains clean, scalable, and maintainable as your application grows. Storing sessions state directly in the managed service will cause massive performance bottlenecks when you attempt to retrieve historical records during peak exam scenarios, violating cloud design guidelines. Let's check your understanding. You are building a collaborative editing feature for a web application using .NET Core. Which service should you choose to leverage built-in support for groups and users, and why? The answer is Azure SignalR service. It provides the high-level abstractions and protocol features that make implementing complex real-time interactions much faster than managing raw WebSockets. Failing to validate JOT tokens on every connection will expose your endpoints to unauthorized access and data leakage during live sessions. To recap, we covered the shift from request response to push-based real-time communication. We explored Azure SignalR service for .NET ecosystems and PubSub for language-agnostic workloads. We compared their protocols and use cases and reviewed best practices like using groups and serverless modes. Both services offload infrastructure complexity, allowing you to focus on delivering value to your users. Misconfiguring the SignalR auth endpoint will immediately break authentication chains and prevent legitimate clients from establishing persistent connections, causing widespread service outages. For the AZ-305 exam, focus on selecting the right service based on the stack and requirements. Know that SignalR is tied to .NET and PubSub is protocol agnostic. Be prepared to identify scenarios where serverless mode saves costs. Also, remember that authentication is critical. Always use JOT tokens to secure your endpoints. Finally, distinguish between using these services for communication versus data storage. Skipping proper cost analysis will lead to unexpected billing spikes when connection limits are exceeded during peak traffic windows. Imagine a massive library where every book sits miles away from the entrance, forcing students to walk that entire distance for a single page. Now picture reading rooms on every floor holding popular copies. Students get information instantly while the main archive stays safe. That is exactly what caching does for your applications. We will explore how caching strategies and Azure CDN reduce latency and protect backend infrastructure. If you skip this design, your database will choke under concurrent load and customers will abandon slow pages. Here is our roadmap for the exam. We start by reviewing core caching strategies like cache aside and write through, so you know which pattern fits your data requirements. Next, we dive into Azure CDN architecture and how requests flow through points of presence. Then, we examine HTTP cache control headers that tell browsers exactly how long to store content. Finally, we wrap up with best practices and specific exam tips for the AZ-305. Misunderstanding these patterns will cost you critical points and cause costly database throttling in production. Let's define a key term that appears frequently in distributed system design: cache aside. This is the most common caching pattern you will encounter. In this strategy, the application code acts as the gatekeeper. When a request comes in, the application first checks the cache. If the data is there, it returns it immediately. If not, it fetches from the database, stores a copy for next time, and returns it to the user. Skipping this pattern will cause repeated database queries that drain CPU resources and trigger throttling alerts during peak traffic. Choosing the right strategy depends on your consistency, requirements versus performance needs. This table compares the three primary approaches you need to know for the exam. Cache aside is lazy and efficient for read-heavy workloads, but risks a cold start. Write through ensures strong consistency by updating both stores simultaneously, though it adds write latency. Time to live defines how long data remains valid before refresh. Picking the wrong balance will cause stale data to surface or overwhelm your backend with unnecessary write operations during traffic spikes. Now let's look at how Azure CDN handles a request. This is a multi-step process that determines whether your user gets a fast response or waits for the origin. We will walk through this workflow step by step to understand where the performance gains happen. Tracking each hop in application insights reveals exactly where latency accumulates, preventing unexpected timeouts when your global audience spikes during peak business hours. When a user initiates a request, the CDN's global routing system immediately directs it to the closest point of presence. This is not a random selection. The DNS resolution ensures the traffic lands at the edge node with the lowest network latency relative to the user's location. This initial hop is crucial because it determines the baseline speed of the response before any caching logic even begins. Misconfigured routing rules will force traffic through distant regions, adding hundreds of milliseconds and violating your service level objectives. Once the request arrives at the edge, the CDN checks its local storage. This is the critical decision point that defines the user experience. The POPI looks for a cached version of the requested asset and validates whether it is still fresh according to the stored metadata. Failing to validate metadata correctly will serve outdated content to browsers, breaking UI components and confusing users who expect real-time updates. This cache validation relies on the HTTP headers we discussed earlier. If the asset is present and the TTL has not expired, the POPI returns the cached version immediately. This is a cache hit. The response time is determined solely by network propagation to the edge, which is typically milliseconds. No backend processing occurs here, preserving your origin resources. Ignoring these headers will force redundant validation checks that waste CPU cycles and increase operational costs across your entire environment. If the cache is empty or stale, the workflow moves to the final phase. The POPI must retrieve the content from your origin, store a copy for future requests, and then deliver it to the user. This step introduces latency, but ensures data freshness. Overlooking this fallback mechanism will cause 404 errors when edge nodes clear their storage, frustrating users who expect uninterrupted access to your published assets. During a cache miss, the POPI forwards the request to your configured origin, such as blob storage or a web app. The origin processes the request and returns the response. The CDN then caches this response based on cache control headers and serves it to the user. Subsequent requests for the same asset will now hit the edge cache, completing the optimization loop. Failing to configure these headers correctly will bypass the entire caching layer, forcing every single click to hit your backend directly. This workflow highlights the core value proposition of CDN design. By moving static content closer to the user, you eliminate the speed-of-light delay associated with distant data centers. The goal is to maximize cache hits at the edge, ensuring that your origin only handles dynamic processing or fresh content requests. Neglecting this principle will cause unnecessary egress fees and saturate your backend servers during traffic spikes, directly impacting your monthly cloud budget. Let's check your understanding of the workflow. Consider a scenario where a popular image expires from the CDN cache at the exact same moment that thousands of users request it. What is the primary risk to your origin server in this situation, and what is the industry term for this phenomenon? Answering this correctly demonstrates your grasp of distributed system design, while missing it reveals a dangerous blind spot regarding backend capacity planning and concurrent request handling. To control how long content stays in the edge cache, you use HTTP headers directly in your application code. This C# example configures a controller action for a product image using the response cache attribute. We set the duration to 3600 seconds and the location to any, ensuring both the browser and Azure CDN cache the response. The no-store flag remains false, confirming caching is allowed. Ignoring these settings will force constant origin fetches that spike latency and inflate your compute costs significantly. Beyond the code, you must monitor the health of your caching strategy. A key metric is the cache hit ratio. If this ratio drops too low, it means your origin server is doing unnecessary work, which increases costs and latency. You should aim for a high hit ratio on static assets. Additionally, always secure your origin by restricting access to only Azure CDN IP ranges. This prevents users from bypassing the cache entirely. Failing to restrict these IPs will expose raw data and defeat your optimization strategy. Let's recap the key takeaways for this lesson. Caching improves performance by moving data closer to the user and reducing backend load. Azure CDN provides global scalability for static assets through points of presence. Cache-aside is the most common application pattern, while TTL-based caching is standard for CDN assets. HTTP headers are your primary mechanism for controlling cache behavior. Always monitor your hit ratio and protect your origin to ensure your strategy delivers the intended gains. Skipping these steps will cause inconsistent user experiences and trigger unexpected throttling during critical business hours. For the AZ-305 exam, focus on these practical tips. You will likely encounter questions about optimizing cache hit ratios using Azure Monitor. Be prepared to identify when to use cache-aside versus write-through based on consistency requirements. Remember that running as CDN endpoint purge can be expensive in terms of performance. It should be used as a last resort for breaking changes, not part of your standard deployment pipeline. Misreading these scenarios will cost you valuable points and reveal gaps in your production readiness knowledge. Imagine managing a fleet of delivery trucks. If you need to change a route or update a schedule, stopping every truck, opening the dashboard, and manually rewiring the controls would grind your business to a halt. App configuration lets you change those settings remotely without ever stopping the engine. This lesson covers how to externalize your settings using Azure App Configuration and use feature flags to decouple deployment from release. You will learn why hard-coding secrets causes production outages and how proper flag management prevents accidental data loss while keeping pipelines reliable. We will start by examining how to externalize configuration using the 12-factor methodology. Then we will define feature flags and compare their distinct types. Next, we will walk through a safe implementation workflow using Python decorators and the as-appconfig kv set command to update a single Boolean flag. Finally, we will cover best practices and common pitfalls like configuration drift that cause exam failures. Mastering this sequence ensures you can architect resilient systems without exposing sensitive credentials during live deployments. Let us define our core term precisely. A feature flag, also known as a feature toggle, is a runtime mechanism that wraps code in a conditional check. This allows you to enable or disable specific features without redeploying the application. It effectively separates the act of deploying code from the decision to release a feature to users. You will use this pattern to safely roll out updates across thousands of instances while preventing untested paths from causing cascading failures in production. Configuration management follows the 12-factor app methodology, which mandates storing config strictly in the environment. You should never hard-code secrets or environment-specific parameters in your source code. Instead, use a layered approach. Start with defaults, override with environment files, and finalize with environment variables. This hierarchy ensures your application behaves consistently across dev, staging, and production while keeping sensitive data out of version control. Failing to externalize settings will expose credentials during audits and break deployments when team members clone the repository locally. Here is a practical example of loading configuration safely. We import the OS module to access environment variables. The appconfig class holds our settings as data fields. In the load config function, we use osgetEnv to fetch values like dbURL and API key with a fallback string for local development. We then validate that critical keys exist, raising an error if they are missing. Finally, we instantiate the config object. This ensures the application fails fast with a clear message if required settings are absent, preventing silent timeouts during high-traffic load testing and keeping your as-appconfig kv set commands secure. Feature flags come in different types, each serving a specific purpose. Release toggles hide unfinished features from users until they are ready. Experimentation toggles enable A/B testing to compare performance between variants. Ops toggles act as circuit breakers to kill a feature causing errors or degradation. Permission toggles restrict features to specific user segments like premium accounts. Understanding these distinctions helps you choose the right tool for your release strategy. Misapplying an ops toggle during a database migration can accidentally roll back critical updates and trigger compliance violations on your exam scenarios. Now let us look at the workflow for implementing feature flags safely. We will use a cumulative reveal to walk through the steps. First, we initialize the configuration provider to fetch flag states from a central store like Azure App Configuration. This initial step establishes the connection endpoint and sets up credential authentication. Skipping this phase causes runtime exceptions when the application attempts to evaluate conditional logic during peak traffic windows. In this code snippet, we initialize the feature provider. The feature provider class connects to a central store like Azure App Configuration or LaunchDarkly. We instantiate it once at startup to ensure we have access to the flag definitions. This setup phase prepares the system to evaluate conditions dynamically based on the current configuration state. Proper initialization prevents memory leaks by caching only the necessary Boolean flags, and avoids latency spikes when processing thousands of concurrent user requests. Next, we wrap the feature logic with conditional checks. This step involves inserting flag evaluations into your code paths to determine which behavior should execute based on the flag state. You will typically use a simple if statement paired with a Boolean return value from your provider. Failing to isolate these checks increases cyclomatic complexity and makes it nearly impossible to track which code branches actually execute during production incidents. Here we wrap the business logic with a conditional check. The process order function calls the provider to get the flag state for a specific user. If the new checkout UI flag is enabled, we run the new logic. Otherwise, we fall back to the legacy path. This pattern allows you to deploy code safely and toggle features on or off at runtime without changing the deployed binary. Incorrectly evaluating this condition can cause duplicate transactions and corrupt your order database during peak sales events. Finally, we enforce default-off safety on failure. This critical step ensures that if the configuration service is unreachable or throws an error, the application defaults to a safe state rather than exposing untested code or crashing. You will implement this by returning false when connection timeouts exceed 3 seconds. Neglecting this fallback mechanism leaves your system vulnerable to cascading failures and violates compliance requirements for high-availability architectures on certification exams. This example demonstrates the safety pattern. The getFlagSafe method wraps the provider call in a try-except block. If the configuration service is unreachable or returns an error, the method catches the exception and returns false by default. This default-off behavior ensures that new features remain disabled during outages, preventing potential crashes or data corruption while keeping the system stable. You must explicitly handle HTTP 503 responses to avoid retry storms that overwhelm your underlying database infrastructure. Remember this principle clearly. Feature flags create technical debt. They are temporary infrastructure that should have a defined lifecycle from creation to cleanup. Always plan for their removal once a feature is fully rolled out to keep your codebase clean and maintainable. Failing to archive these toggles after 90 days causes configuration bloat, slows down deployment pipelines, and creates audit failures during security reviews of your production environment. For instance, deleting the payment gateway toggle immediately after launch prevents orphaned records from accumulating in Azure app configuration. Let us check your understanding quickly. Where should database connection strings be stored in a production application? A. Hard-coded in the source code repository. B. In environment variables or a secrets manager. C. In a local configuration file committed to Git. D. In the feature flag store only. The correct answer is B. Storing credentials externally prevents accidental exposure through version control and ensures compliance with Azure Key Vault standards during certification exams. To recap, externalize your configuration to decouple settings from code. Use feature flags to control releases at runtime without redeploying. Implement flags safely by initializing providers, wrapping logic with conditionals, and enforcing default-off states on failure. Always validate configuration at startup and clean up flags promptly to avoid technical debt. Mastering these steps prevents configuration drift and ensures your architecture passes the AZ-305 scenario questions regarding secure deployment pipelines. For the AZ-305 exam, focus on these key areas immediately. Know how to configure Azure app configuration and manage secrets securely using managed identities. Understand the different types of feature flags and their specific use cases. Be prepared to identify pitfalls like flag hell and performance impacts from excessive config calls. Always choose centralized stores for consistent state across distributed systems to avoid data inconsistency during failover events. Imagine a restaurant kitchen with only one stove. One complex order slows everything down. Add more stoves, and you handle more orders simultaneously without losing speed. That is the essence of scalability in cloud architecture. In this lesson, we will explore how to design systems that grow seamlessly under load while maintaining high performance. We will configure Azure App Service Autoscale profiles with concrete CPU thresholds, ensuring your web apps automatically provision additional instances before latency spikes. If you skip this step, a sudden traffic burst will crash your primary server and trigger immediate downtime. We will start by comparing vertical and horizontal scaling approaches. Then we will dive into stateless architecture and asynchronous processing. Next, we will cover database patterns like sharding and read replicas. Finally, we will review best practices for failure design and monitoring. You will learn to run the as-vm resize command for vertical expansion and use as-axscale for horizontal node pools. Mastering these commands prevents resource exhaustion during peak exams. If you misconfigure node counts, your cluster will throttle requests and trigger cascading service failures across dependent microservices. Vertical scaling means adding more power to an existing machine, like upgrading CPU or RAM. It has a physical ceiling and creates a single point of failure. Horizontal scaling adds more machines to the pool. This is the cloud-native standard, offering virtually infinite growth and better fault tolerance. A key metric: horizontal scaling can improve fault tolerance by up to 90% compared to a single large instance. Always prefer scale-up operations for legacy monoliths, but deploy scale-out with Azure Front Door for modern IPIs. Misjudging instance limits will cause memory leaks to crash the entire tenant environment. Let's compare these approaches. Vertical scaling is simpler to implement, but hits a hardware ceiling and risks downtime during upgrades. Horizontal scaling requires load balancing and stateless design, but offers elastic growth and high availability. For cloud-native apps, horizontal is almost always the target. Configure an auto-scale rule with a minimum of 2 instances and a maximum of 8 to guarantee redundancy. Skipping this baseline configuration leaves your application vulnerable to single-node outages that immediately drop all active user sessions. Now let's design a scalable system. First, we externalize state to ensure servers are stateless. This allows any server to handle any request without losing context. Store all session tokens in Azure Cache for readies using the setx command with a 360-second timeout. Externalizing state prevents data loss during automatic instance reboots. If you keep sessions in local memory, rolling deployments will silently invalidate active logins and frustrate every concurrent user. Here is how statelessness looks in code. The function checks a ready's cache for user data. If found, it returns immediately. If not, it queries the database and caches the result. This keeps the server lightweight and allows requests to be routed to any instance. Implement a getOr-default pattern that validates cache hits against a 5-millisecond timeout threshold. Failing to implement timeout logic will cause thread pool exhaustion when the cache endpoint becomes temporarily unreachable. Next, we offload heavy processing. Instead of blocking the main thread, we push tasks to a background queue. This keeps the IPI responsive and allows workers to process items at their own pace. Route these background jobs through Azure Service Bus with a visibility timeout set to 90 seconds. Offloading work prevents synchronous request timeouts from crashing your web tier. Ignoring queue depth limits will cause message duplication and trigger duplicate charge errors in payment systems. This code demonstrates asynchronous processing. The order is saved to the database, then a message is pushed to a queue for email sending. The function returns success immediately, freeing the thread to handle other requests while the worker processes the email. Configure the Azure function consumer with a maximum of 20 concurrent executions per instance. Running too many workers simultaneously will overwhelm downstream EAS-MTP servers and trigger rate limit throttling across your entire notification pipeline. Finally, we cache data aggressively. We identify hot data and store it at multiple layers, from the browser to the application level, to avoid expensive database queries. Implement HTTP caching headers with a max age of 300 seconds for static product listings. Aggressive caching reduces backend compute costs by up to 70%. Neglecting cache invalidation strategies will serve stale pricing information to customers and trigger severe revenue reconciliation discrepancies. This Redis cache example shows the pattern in action. We check for cached data first. If missing, we query the database and set the result with an expiration time. This reduces latency and protects the database from heavy read loads. Use the EX flag with a 240-second TTL during every write operation to guarantee eventual consistency. Failing to apply proper TTL values will cause cache stampedes that instantly saturate your primary SQL Server connection pool. For databases, use read replicas for read-heavy workloads. Direct select queries to replicas, keeping the primary free for writes. For write-heavy loads, implement sharding to partition data across multiple instances based on a shard key, distributing the write pressure. Configure Azure SQL Elastic pools with exactly 3 managed instances per region to balance query distribution. Misrouting write operations to replica endpoints will trigger strict read-only exceptions and immediately halt your transaction processing pipeline. Remember this key principle: design for failure. Assume servers will crash. Use auto-scaling groups and multi-IZ deployments to ensure availability even when hardware fails. Deploy your application across 3 distinct availability zones with a minimum of 2 virtual machines per zone. Relying on single-zone infrastructure leaves your platform completely exposed to regional network partitions that will instantly sever all user connections. Quick check: which strategy externalizes session data to enable horizontal scaling? The answer is statelessness, where session data is stored in a distributed cache like Redis rather than local memory. Configure your web role to authenticate against a centralized Azure ID tenant instead of maintaining local cookies. Failing to centralize authentication will cause inconsistent permission checks across scaled instances and grant unauthorized access to sensitive customer records. For the exam, focus on stateless design and asynchronous processing. Know when to use read replicas versus sharding. Understand how CDNs reduce latency for static assets. And always consider observability. You cannot scale what you cannot measure. Enable Azure Monitor with a 20-second metric aggregation interval and configure alert rules at 90% CPU utilization. Ignoring these telemetry thresholds will mask gradual performance degradation until your application completely stops responding to live traffic. We covered scaling strategies, stateless architecture, database patterns, and best practices. Key takeaways: externalize state, offload processing, cache aggressively, use read replicas and sharding for databases, and build with observability in mind. Apply these patterns consistently across your Azure Kubernetes service clusters to maintain predictable performance under stress. Skipping observability integration will leave you blind during peak load events and prevent accurate capacity planning for future exam scenarios. Imagine running a hotel where every room has its own dedicated staff and maintenance team, but no central manager to coordinate them. You would face chaos and wasted resources while guests struggle for help. Azure Container Apps acts as that central manager. It delivers container power without the operational nightmare of managing underlying infrastructure. When you run the as container wrap create command, the platform automatically provisions networking and scaling rules. This eliminates manual orchestration errors that cause downtime, ensuring you focus purely on shipping code instead of fighting cluster patches. We will start by mapping the core architecture of container apps, focusing on environments and immutable revisions. Next, we will examine how K-EDA and Dapr enable advanced scaling and service patterns through real CLI workflows. Then we will walk through a complete deployment procedure using the Azure CLI to provision resources. Finally, we will review critical best practices for security, health probes, and observability. Missing these configurations causes production outages and fails the AZ-305 exam because test designers expect precise scaling thresholds and secure networking boundaries. Let's start with the definition. Azure Container Apps is a fully managed serverless container service built directly on Kubernetes, K-EDA, and Dapr. Unlike traditional clusters where you manually manage nodes and apply patches, ICI completely abstracts that complexity away. When you push an image to a registry and deploy it via the CLI, the platform automatically handles infrastructure provisioning, scaling, and internal networking. Skipping this managed layer causes configuration drift and unexpected billing spikes when developers accidentally leave idle compute running. To understand where Container Apps fits, compare it directly to Azure Kubernetes Service. With IKS, you manage the control plane and worker nodes, requiring significant operational overhead for patching and network policies. Container Apps is fully managed. You only define container specs and scaling rules in a YAML file. The cost model differs. IKS charges for underlying VMs, while ICI charges per vCPU and memory second with automatic scale-to-zero capabilities. Confusing these models leads to massive overprovisioning costs during low-traffic periods. Now let's look at the architecture. The top-level boundary is the environment, which acts as a secure logical cluster where apps share the same virtual network and log analytics workspace. Inside that environment, you deploy individual container apps. Each app maintains multiple revisions, which are immutable snapshots of your container configuration. This revision system enables precise traffic splitting, allowing you to route exactly 20% of requests to a new version for safe blue-green deployments without disrupting active users. Let's move to a practical procedure. We will design and deploy a scalable microservice step by step using real CLI commands. First, we provision the secure environment inside your target resource group. This initial step establishes the networking layer and diagnostic workspace before any application code touches the platform. Skipping this foundational step causes deployment failures because subsequent container resources require an existing environment reference to attach their routing rules and logging endpoints properly. We start by creating the environment using the Azure CLI command as container wrap env create. This command provisions the logical cluster in the East US region while automatically attaching a dedicated log analytics workspace. You must specify the exact resource group and environment name before execution. The platform instantly creates the underlying networking and logging infrastructure for you, eliminating manual subnet configuration that typically causes IP conflicts and routing failures during multi-service deployments. Next, we deploy the container app itself by defining the exact container image and setting precise scaling rules based on HTTP concurrency. You will configure the minimum replica count to prevent cold start latency during traffic spikes. This step establishes the compute boundary for your workload, ensuring that misconfigured thresholds Do not trigger aggressive scale-out events that exhaust your subscription limits or cause sudden billing surprises. Here is the actual command to deploy the app using as-container-app create. We link it directly to the environment we just created and point the image to a public registry. We set the target port to 8000 and enable external ingress so users can reach it. Crucially, we configure scaling rules with a minimum of 1 replica to avoid cold starts, a maximum of 10 replicas, and a concurrency threshold of 50 requests per replica. Finally, we configure security boundaries and health probes directly in the YAML definition. We assign a system-assigned managed identity to avoid storing plaintext secrets in code, and we define strict liveness and readiness probes to ensure routing traffic only reaches healthy containers. Skipping these checks causes premature traffic routing that triggers cascading failures when unhealthy pods attempt to process live requests without proper circuit breakers. For the final configuration, we use a YAML definition file that explicitly enables managed identity and references external key vault references for secrets. We define environment variables to inject credentials securely instead of hard-coding them directly into the deployment manifest. The liveness probe checks the health endpoint every 10 seconds after an initial delay period. This precise timing ensures the platform accurately detects stalled processes before routing live customer traffic to frozen containers. Let's deepen our understanding of the scaling engine. Container Apps includes built-in support for KEDA, which stands for Kubernetes Event-Driven Autoscaling. This allows your applications to scale dynamically based on external events, such as processing queue depth in Azure Service Bus or monitoring lag in a Kafka topic, rather than relying solely on CPU metrics. A critical exam fact is that ICI scales down to 0 replicas, meaning you incur 0 compute charges during idle periods for intermittent batch workloads. Quick check: you are designing a microservice that processes orders from an Azure Service Bus queue where traffic is highly bursty and completely unpredictable. Should you use standard HTTP concurrency scaling or KEDA event-driven scaling to handle the load efficiently? Think about it for a moment before proceeding. Choosing the wrong trigger type causes severe latency spikes during peak processing windows while wasting compute resources during quiet intervals, directly impacting your SLI compliance and monthly cloud spend. The answer is KEDA. Now let's define a critical security concept: managed identity. In container apps, you should always assign Azure managed identities to access dependent resources like Key Vault or SQL database securely. This grants the container app precise permissions without storing plaintext connection strings or secrets in your code or configuration files. Failing to implement this pattern exposes sensitive credentials to version control repositories and violates strict compliance, auditing standards required for enterprise deployments. Health probes are essential for system reliability. Container Apps supports 3 distinct types: liveness, readiness, and startup. Liveness determines if the container should be restarted. If it fails repeatedly, the platform automatically kills the process. Readiness determines if the container can receive traffic. If it fails, active connections are gracefully drained. Startup acts as a delayed liveness check that only applies during initialization, preventing premature restarts during slow application boot sequences. Here is a pro tip for security architecture. Always enable ingress only when absolutely necessary for external access. If your service acts as a backend worker that does not need to be accessed from the public internet, keep the ingress configuration strictly disabled. This reduces your attack surface significantly and prevents unauthorized IPI calls from reaching sensitive endpoints, which is a critical design principle for passing security-focused certification scenarios. Let's recap the key takeaways for your exam preparation. First, ICI abstracts Kubernetes management while providing powerful scaling via K-EDA and service patterns via Dapper. Second, leverage event-driven scaling to match costs precisely to demand, including automatic scale-to-zero capabilities. Third, use immutable revisions for safe deployment strategies like canary releases. Fourth, secure your apps with managed identities and private networking. Finally, implement robust observability using log analytics and application insights to catch failures early. For the AZ-305 exam, focus heavily on architectural design decisions rather than memorization. Know exactly when to choose container apps over IKS based on management overhead and specific scaling requirements. Understand the functional difference between liveness and readiness probes during failure scenarios. Be prepared to identify correct K-EDA trigger types for different workloads. Finally, remember that environments provide the secure boundary and shared networking context required for compliant multi-service deployments.